streaming. I decided to keep writing the articles, keep reviewing the articles until I have a bunch of them. Then after that, I will decide what I'm gonna do. I think I'm gonna start now with the Italian thing. I'm gonna spend 1 hour, then take a break, then continue. I'll do the Italian thing first, then I'm gonna review this bagging, and then I'm gonna review cart and CatBoost.
Fa,
Fa,
does,
fisso,
fisso,
set, unchanging,
3,
3,
3,
desiderare,
desiderare,
desire,
aria,
aria,
air,
bene,
bene,
well,
anche,
anche,
also,
giocare,
giocare,
play,
piccolo,
piccolo,
small,
fine,
fine,
end,
mettere,
mettere,
put,
casa,
casa,
home,
leggere,
leggere,
read,
mano,
mano,
hand,
portare,
portare,
carry,
grande,
grande,
large,
compitare,
compitare,
spell, words,
aggiungere,
aggiungere,
add,
anche,
anche,
even, also,
terra,
terra,
land,
qui,
qui,
here,
devo,
devo,
I must,
grande,
grande,
big,
alto,
alto,
high, tall,
tale,
tale,
such,
seguire,
seguire,
follow,
atto,
atto,
enact,
perché,
perché,
why,
chiedere,
chiedere,
ask,
maschi,
maschi,
men,
cambiamento,
cambiamento,
a change,
è andato,
è andato,
he, she went,
luce,
luce,
light,
tipo,
tipo,
kind, of thing,
spento,
spento,
turned off,
bisogno,
bisogno,
need,
casa,
casa,
house,
immagine,
immagina,
image,
provare,
provare,
try,
noi,
noi,
us,
di nuovo,
di nuovo,
again,
animale,
animale,
animal,
punto,
punto,
point,
madre,
madre,
mother,
mondo,
mondo,
world,
vicino,
vicino,
near,
costruire,
costruire,
build,
se stesso,
se stesso,
himself,
terra,
terra,
earth,
padre,
padre,
father,
Machine learning algorithms have been a hot topic in recent years, with numerous advancements and innovations being made to enhance their capabilities and performance. One such algorithm that has gained significant attention is the bagging algorithm. Dive into what the bagging algorithm is, how it works, and its various applications. I think I'm gonna change this. think I'm just gonna put this. Actually, bagging stands for bootstrapped aggregation and refers to a simple ensemble learning technique that involves combining the results of several base models to improve the overall performance of the model. Simple terms, it's a method of combining multiple models to create a single, more accurate model. The bagging algorithm works by training several base models on different subsets of the training data. These subsets are obtained by randomly selecting data points from the original dataset with replacement. This means that some data points may be repeated multiple times in the subset, while others may not be included at all. Once the base models have been trained, their predictions are combined to form the final prediction for a new input. The combination of predictions can be done in various ways, such as taking the average majority vote or weighted average of the predictions. One of the primary advantages of the bagging algorithm is that it reduces overfitting, a common problem in machine learning models where the model becomes too complex and memorizes the training data, leading to poor generalization performance on new data. By training multiple base models on different subsets of the training data, the bagging algorithm helps to reduce overfitting and improve the overall performance of the model. Another advantage of the bagging algorithm is that it can handle high-dimensional data and complex relationships between features. This is because the base models are trained on different subsets of the training data, which helps to reduce the impact of noise and outliers in the data. There's a wide range of applications, proven performance of decision trees, linear regression models, neural networks, reducing the variance in random forests. As estimators, Bayes estimators, random states. It comes from scikit-learn. No, sklearn. This is so it seems like it is correct, I think. I don't know what this thing does, but it's from the library. Oh no, it's not from the library. This one is from the library. So I guess it's just like a seed for a random state, probably. Alright, so this is the thing, I don't know how this works. But I think it's just creating a matrices with the getting random points of the data. That's what's doing. So it's getting random points to test on each iteration. And then it appends everything on the estimators. Yeah, so I think this is correct. It's just like it says that now I'm obviously gonna check to see if that's the point of the algorithm, but I think that I understand. It's like breaking down the prediction in a randomized way in the data points. So we make several different predictions, and then the overall prediction is going to be the combination of all the predictions we made. The bagging algorithm is a powerful and versatile machine learning technique that can improve the performance of various models. By training multiple base models on different subsets of the training data, it reduces overfitting and enhances the overall performance of the model. Whether you're working on a classification or a regression problem, the bagging algorithm is definitely worth considering. So the thing is, like I said before many times, I think I'm not gonna I wanna spend at least because it's a very, not very risky, but it is a risky thing doing this thing because I don't know, because of ChatGPT and the whole Bing thing, if SEO is going to be even a thing or if blogging is going to be even a thing, because there is more likely that it's going to be just a bunch of machine learning models serving data to people in the future, which is very dangerous, but it looks like that's the direction things are going. So I'm not really sure, like, if this is worth my time or not. So I think it is worth because I am learning a bunch of stuff while I do it, but I don't want to spend so much time on each article that the risk of spending all the time without getting any return is sure great. So I'd rather just do a bunch of articles, and then if it doesn't work, the worst that happens is I learned a bunch of stuff along the way and then can build something else. But if I spend a bunch of time perfecting each article, then it might be just a huge waste of time. So I'm just gonna try to go fast through all of them. Just verify on these ones if it is correct or not.
Bagging in machine learning, step to perform and its advantages. Ensemble learning methods help improve the accuracy of classification and regression models. What is ensemble learning? Ensemble learning is a widely used. What is bagging in machine learning? Bagging, also known as bootstrap aggregating, is an ensemble learning technique that helps to improve the performance and accuracy of machine learning algorithm. It is used to deal with bias variance trade-offs and reduces the variance of a prediction model. Bagging avoids overfitting of data and is used for both regression and classification models, specifically for decision tree algorithm. What is bootstrapping? Bootstrapping is the method of randomly creating samples of data out of a population with replacement to estimate a population parameter. Steps to perform bagging. Consider there are n observations and m features in the training set. You need to select a random sample from the training dataset without replacement. A subset of m features is chosen randomly to create a model using sample observations. The feature offering the best split out of the lot is used to split the node. The tree is grown, so you have the best root nodes. The above steps are repeated n times. It aggregates the output of individual decision trees to give the best predict. Bagging minimizes the overfitting of data. It improves the model's accuracy. It deals with higher dimensional data efficiently. Become an expert in all things AI and ML. Caltech postgraduate program in AI and ML Explorer program. Bagging demonstration in Python using Iris dataset. Import the libraries. Load the dataset. Split the dataset into training and testing. Creating subsamples to train model. Define a decision tree. Classification model for bagging. Train models and print their accuracy. Print the mean accuracy. Display the model's accuracy. From the above demonstration, you can conclude that the individual models, weak learners, overfeed the data and have a high variance. But the aggregated result has a reduced variance and is trustworthy. Accelerate your career in AI and ML with the AI and Machine Learning course with Purdue University collaborated with IBM. Conclusion. Bagging is a crucial concept in statistics and machine learning that helps to avoid overfitting of data. It is a model averaging procedure that is often used with decision trees but can also be applied to other algorithms. Want to become an AI engineer? Look no further. Caltech postgraduate program in AI and ML Explorer program. We hope this article helped you understand the importance of bagging in machine learning. Do you have any questions related to this article? If you do, feel free to share the questions with us by placing them in the comments section of this page. Our team would be happy to review and help you out with resolutions as soon as possible. To get started with machine learning, click on the following link, AI and Machine Learning Certification. About the author. Ava Heath is a senior research analyst at Simplelearn. Passionate about data analytics, machine learning, and deep learning, Ava Heath is also interested in politics, cricket, and football. Recommended programs. Caltech postgraduate program in AI and Machine Learning. 2,511 learners. Lifetime access star. Professional certificate program in AI and Machine Learning.
Yeah, so it is just like I said. You're just getting random samples of the data on each iteration, and then appending to the estimators, and then looping through the estimators, making predictions, and then getting the average of the predictions. It's pretty self-explanatory. Getting the mean of the predictions, not the average. And then it rounds the results and returns it. So pretty easy to understand. I think I'm gonna read this one more, and then move on to the next one.
Learn how bootstrap aggregating or bagging can improve the accuracy of machine learning models, enabling you to develop insights. Bagging, also known as bootstrap aggregation, is the ensemble learning method that is commonly used to reduce variance within an OED dataset. In bagging, or random sample data and train selected replacement, meaning that individual data points can be chosen only once. After selecting samples are generated, these weak models are then trained independently and depending on type class. Commercial classification, for example, the average point of predictions yield a more accurate estimate. As a note, the random forest algorithm is a specific extension of the bagging method. Using the bagging, a feature of this creating a non-correlated.
Aided forest of decision tree. Ensemble learning. Ensemble learning gives credence to the idea of the wisdom of crowds, which suggests that the decision-making of a larger group of people is typically better than that of an individual expert. Similarly, ensemble learning refers to a group, or ensemble, of base learners, or models, which work collectively to achieve a better final predict. A single model, also known as a base or weak learner, may not perform well individually due to high variance or high bias. However, when weak learners are aggregated, they can form a strong learner, as their combination. Ensemble methods are frequent. Remember, when an algorithm overfits or while decision trees can exhibit high bagging versus boosting. Bagging and boosting are two main types of ensemble learning methods. As highlighted in this study, PDF, 248 KB, this link resides outside of IBM.com. The main difference between these learning methods is the way in which they are trained. In bagging, weak learners are trained in parallel, but in boosting, they learn sequentially. This means that a series of models are constructed, and with each new model iteration, the weights of the misclassified data in the previous model are increased. This redistribution of weights helps the algorithm identify the parameters that it needs to focus on to improve its performance. AdaBoost, which stands for Adaptative Boosting Algorithm, is one of the most popular boosting algorithms as it was one of the first of its kind. Other types of boosting algorithms include XGBoost, Gradient Boost, and Brown Boost. Another difference in which bagging and boosting differ are the scenarios in which they are used. For example, bagging methods are typically used on weak learners which exhibit high variance and low bias, whereas boosting methods are leveraged when low variance and high bias is observed. In 1996, Leo Bremen, PDF, 829 KB, this link resides outside of IBM.com, introduced the bagging algorithm, which has three basic steps. Bootstrapping. Bagging leverages a bootstrapping sampling technique to create diverse sample. This resampling method generates different subsets of the training dataset by selecting data points at random and with replacement. This means that each time you select a data point from the training dataset, you are able to select the same instance multiple times. As a result, a value/instance repeated twice, or more, in a sample. Parallel training. These bootstrap samples are then trained independently and in parallel with each other using weak or base learner. Aggregation. Finally, depending on the task, i.e. regression or classification, an average or a majority of the predictions are taken to compute a more accurate estimate. In the case of regression, an average is taken of all the outputs predicted by the individual classifiers. This is known as soft voting. For classification problems, the class with the highest majority of votes is accepted. This is known as hard voting or majority vote. There are a number of key advantages and challenges that the bagging method presents when used for classification or regression problems. The key benefits of bagging include ease of implementation. Python libraries such as scikit-learn, also known as sklearn, make it easy to combine the predictions of base learners or estimators to improve model performance. Their documentation, link resides outside IBM, lays out the available modules that you can leverage in your model optimization. Reduction of variance. Bagging can reduce the variance within a learning algorithm. This is particularly helpful with high-dimensional data, where missing values can lead to higher variance, making it more prone to overfitting and preventing accurate generalization to new dataset. The key challenges of bagging include loss of interpretability. It's difficult to draw very precise business insights through bagging because due to the averaging involved across prediction. While the output is more precise than any individual data point, a more accurate or complete dataset could also yield more precision within a single classification or regression model. Computationally expensive. Bagging slows down and grows more intensive as the number of iterations increase. Thus, it's not well suited for real-time application. Clustered systems or a large number of processing cores are ideal for quickly creating bagged ensembles on large test sets. Less flexible. As a technique, bagging works particularly well with algorithms that are less stable. One that are more stable or subject to high amounts of bias do not provide as much benefit as there's less variation within the dataset of the model. As noted in the hands-on guide to machine learning, link resides outside of IBM. Bagging a linear regression model will effectively just return the original predictions for large enough B. The bagging technique is used across a large number of industries, providing insights for both real-world value and interesting perspectives, such as in the Grammy debates with Watts. Key use cases include healthcare. Bagging has been used to form medical data predictions. For example, research, PDF, more specifically, IT. Meanwhile, environment, more specific, finance, this research, this study, related solution, IBM SPSS, Watson,
Classification and regression trees is a popular machine learning algorithm that is used for both regression and classification tasks. The algorithm is simple, fast, and has a low computational cost, making it a great option for both small and large datasets. This article provides a comprehensive guide to CART and covers everything from the basics to advanced topics, making it the ultimate resource for anyone looking to learn about CART. CART is a type of decision tree algorithm that is used for solving both regression and classification problems. It's called a decision tree because it models decisions and decisions that lead to specific consequences. Similar to decision making in real life. In machine learning, the tree models are used to predict a target variable by using a set of input variables. In CART, the data is split into smaller subsets known as nodes, and a decision is made at each node to determine which path the data should take. This process continues until a stopping criterion is met, such as a minimum number of samples required in a node or reaching a maximum tree depth. The final result of the CART algorithm is a tree structure that represents the relationship between the input variables and the target variable. It's easy to understand and implement, making it a great option for both beginners and experts. It's for both regression and classification problems, making it a versatile option for a wide range of problems. Computational cost, interoperability. CART algorithms works by recursively splitting the data into smaller subsets known as nodes until a stopping criterion is met. The algorithm starts by selecting the best variable and split point to maximize the separation between the target variable. This process is repeated at each node until the stopping criterion is met. The final result is a tree structure that represents the relationship between the input variables and the target variable. One important factor in the CART algorithm is the selection of the best variable and split point. There are several methods for selecting the best variable and split point, including the Gini index and information gain. This is also part of the first one that CatBoost, I think. This is Gini index. Measures the impurity of the data at a node, and the information gain measures the reduction in entropy from splitting the data at a node. Regression, classification, feature selection, outlier detection. Regression is when you're trying to separate the data points. You like using the algorithm for that, the different data points on the data set. You're trying to create a boundary between them. And classification is when you want to determine two different categories, like cats or dogs, I think. So you don't want to separate the data points, you want to create a prediction of what it is, I think. I'm gonna search that.
Regression versus classification. What's the difference? Machine learning algorithms can be broken down into two distinct types, supervised and unsupervised learning algorithm. Supervised learning algorithms can be further classified into two types. One, regression. The response variable is continuous. For example, the response variable could be weight, height, price, time, total units. In each case, a regression model seeks to predict a continuous quantity. Regression example. Suppose we have a data set that contains 3 variables for 100 different houses: square footage, number of bathrooms, and selling price. We could fit a regression model that uses square footage and number of bathrooms as explanatory. We could then use, this is an example. The most common way to measure the accuracy of a regression model is by calculating the root mean square error, RMSE, a metric that tells us how far apart our predicted values are from our observed values. It is calculated as RMSE equals square, where sigma is a fancy symbol that means sum. Pi is the predicted value for the ith observation. Oi is the observed value for the ith observation. N is the sample size. The smaller the RMSE, the better a regression model is able to fit the data. 2. Classification. The response variable is categorical. For example, the response variable could take on the following values: male or female, pass or fail, low, medium. In each case, a classification model seeks to predict some class label. Classification example. Suppose we have a data set that contains 3 variables for 100 different college basketball players: average points per game, division level, and whether or not they got drafted into the NBA. We could fit a classification model that uses average points per game and division level as explanatory variables and drafted as the response variable. We could then use this model to predict whether or not a given player will get drafted into the NBA. This is an example of a class. That is, the most common way to measure the accuracy of a classification model is by simply calculating the percentage of correct classifications the model makes. Accuracy equals correction classification slash total attempted classifications asterisk 100%. For example, accuracy equals the higher the similarities. Regression and classification algorithms are similar in the following. Both are supervised learning algorithms, i.e. they both use one or more explanatory variables to build models to predict some. Both can be used to understand how changes in the values of explanatory variables affect the values. Differences between regression and regression algorithms seek to predict a continuous quantity, and classification algorithms seek to predict a class label. The way we measure the accuracy of regression and classification models differ. It's worth noting that a regression problem can be converted into a classification problem by simply discretizing the response variable into. We could build a regression. However,
That's exactly what I said and what I was thinking.
CART, classification and regression tree, in machine learning. CART, classification and regression tree, is a variation of the decision tree algorithm. It can handle both classification and regression tasks. Scikit-learn uses the classification and regression tree, CART, algorithm to train decision trees, also called growing trees. CART was first produced by Leo Breman, Jerome Friedman, Richard Olshan, and Charles Stone in 1984. CART algorithm. CART is a predictive algorithm used in machine learning, and it explains how the target variable's values can be predicted based on other matter. It is a decision tree where each fork is split into a predictor variable and each node has a prediction for the target variable at the end. In the decision tree, nodes are split into subnodes on the basis of a threshold value of an attribute. The root node is taken as the training set and is split into 2 by considering the best attribute and threshold value. Further, the subsets are also split using the same logic. This continues till the last pure subset is found in the tree or the maximum number of leaves possible in that growing tree. The CART algorithm works via the following process. The best split point of each input is obtained. Based on the best split points of each input in step 1, the new best split point is identified. Split the chosen input according to the best split point. Continue splitting until a stopping rule is satisfied or no further desirable splitting is available. CART algorithm uses Gini impurity to split the data set into a decision tree. It does that by searching for the best homogeneity for the subnodes, with the help of the Gini index criteria. Gini index / Gini impurity. The Gini index is a metric for the classification tasks in CART. It stores the sum of squared probabilities of each class. It computes the degree of probability of a specific variable that is wrongly being classified when chosen randomly in a variation of the Gini coefficient. It works on categorical variables, provides outcomes either successful or failure, and hence conducts binary splitting only. The degree of the Gini index varies from 0 to 1. Where 0 depicts that all the elements are allied to a certain class, or only one class exists there. The Gini index of value 1 signifies that all the elements are randomly distributed across various classes, and a value of 0.5 denotes the elements are uniformly distributed into some classes. Mathematically, we can write Gini impurity as follows, where pi is the probability of an object being classified to a particular class. Classification tree. A classification tree is an algorithm where the target variable is categorical. The algorithm is then used to identify the class within which the target variable is most likely to fall. Classification trees are used when the dataset needs to be split into classes that belong to the response variable, like yes or no. Regression tree. A regression tree is an algorithm where the target variable is continuous and the tree is used to predict its value. Regression trees are used when the response variable is continuous. For example, if the response variable is the temperature of the day. Pseudocode of the CART algorithm: d equals 0, and tree equals 0. Note, 0 equals 1, node 1 equals 0, node 2 equals 0. While end tree. CART models are formed by picking input variables and evaluating split points on those variables until an appropriate tree is produced. Steps to create a decision tree using the CART algorithm. Greedy algorithm. In this, the input space is divided using the greedy method, which is known as a recursive binary splitting. This is a numerical method within which all of the values are aligned and several other split points are tried and assessed using a cost function. Stopping criterion. As it works its way down the tree with the training data, the recursive binary splitting method described above must know when to stop split. The most frequent halting method is to utilize a minimum amount of training data allocated to every leaf node. If the count is smaller than the specified threshold, the split is rejected and also the node is considered the last leaf node. Tree pruning. Decision trees complexity is defined as the number of splits in the tree. Trees with fewer branches are recommended as they are simple to grasp and less prone to cluster. Working through each leaf node in the tree and evaluating the effect of deleting it using a holdout test set is the quickest and simplest pruning approach. Data preparation for the CART. No special data preparation is required for the CART algorithm. Advantages of CART. Results are simplistic. Classification and regression trees are non-parametric and non-linear. Classification and regression trees implicitly perform feature selection. Outliers have no meaningful effect on CART. It requires minimal supervision and produces easy to understand model. Overfitting. High variance. Low bias. The tree structure may be unstable. Applications of the CART algorithm. For quick data insights. In blood donors classification. For environmental and ecological data. In the financial sector. Getting started. Machine learning. CART. Classification and regression trees for clean but powerful models. How does the CART algorithm work, and how to successfully use it in Python?
Training the CART model involves several steps. Prepare the data. This includes cleaning the data, handling missing values, and transforming variables as necessary. Split the data. Blah, blah, blah. Training the CART model. Evaluate the model. Fine-tune the model. Seems correct. And this is the node of the tree.
A simple and clear explanation of the Gini impurity. Ask question. Asked. 5 years, 4 months ago. Modified. 1. Begin group. Is there an easy explanation of this? CART intuition Gini. Share a link to this question. Copy link CC by SA.
I think I get it. I think the code here is correct, it's just incomplete because of these methods here. But I think I'm gonna leave it like this, to be honest, and the rest here doesn't matter as well. I don't want to spend a lot of time on this one. So I'm gonna read 2 more articles just to see if I think that the articles have something that contradicts this one, then I'm gonna review or think about it more. Is the searching the tree here based on the threshold value?
A classification and regression tree, CART, algorithm. Introduction. Machine learning has been one of the most rapidly advancing topics to study in the field of artificial intelligence. There are a lot of algorithms under machine learning that have specifically gained popularity due to their transparent nature. One of them is the decision tree algorithm, popularly known as the classification and regression trees, CART, algorithm. A classification and regression tree, CART, algorithm. Introduction. Machine learning has been one of the most rapidly advancing topics to study in the field of artificial intelligence. There are a lot of algorithms under machine learning that have specifically gained popularity due to their transparent nature. One of them is the decision tree algorithm, popularly known as the classification and regression trees, CART, algorithm. The CART algorithm is a type of classification algorithm that is required to build a decision tree on the basis of Gini's impurity index. It is a basic machine learning algorithm and provides a wide variety of use cases. A statistician named Leo Breeman coined the phrase to describe decision tree algorithms that may be used for classification or regression predictive modeling issues. CART is an umbrella word that refers to the following types of decision trees. Classification trees. When the target variable is continuous, the tree is used to find the class into which the target variable is most likely to. Regression trees. These are used to forecast the value of a continuous variable. In this article, we will discuss decision trees, the CART algorithm and its different models, and the advantages of the CART algorithm. Understanding decision tree. A decision tree is a technique used for predictive analysis in the fields of statistics, data mining, and machine learning. The predictive model here is the decision tree, and it is employed to progress from observations about an item that is represented by branches and finally concludes at the item's target value, which is represented in the leaf. Because of their readability and simplicity, decision trees are among the most popular machine learning methods. The structure of a decision tree consists of 3 main parts: root nodes, internal nodes, and leaf node. Decision tree structure, image source. As shown in the diagram, the first node or the root node is the training dataset, followed by the internal node and leaf node. The internal node acts as the decision-making node, as this is the point at which the node divides further based on the best feature of the subgroup. The final node or the leaf node is the one that holds the decision. Must read. CART algorithm. In the decision tree, the nodes are split into subnodes on the basis of a threshold value of an attribute. The CART algorithm does that by searching for the best homogeneity for the subnodes, with the help of the Gini index criteria. The root node is taken as the training set and is split into 2 by considering the best attribute and threshold value. Further, the subsets are also split using the same logic. This continues till the last pure subset is found in the tree or the maximum number of leaves possible in that growing tree. This is also known as tree proof. Calculating Gini index. The formula of Gini index. Here, C is the total number of classes and P is the probability of class I. Related blog, AUC route curve tutorial. CART models from data. CART models are formed by picking input variables and evaluating split points on those variables until an appropriate tree is produced. According to machine learning master, let us look at the steps required to create a decision tree using the CART algorithm. Greedy algorithm. The input variables and the split points are selected through a greedy algorithm. Constructing a binary decision tree is a technique of splitting up the input space. A predetermined ending condition, such as a minimum number of training examples given to each leaf node of the tree, is used to halt tree building. The input space is divided using the greedy approach. This is known as recursive binary splitting. This is a numerical method in which all of the values are aligned and several split points are tried and assessed using a cost function, with the split with the lowest cost being chosen. The cost function that is reduced to determine split points for regression predictive modeling problems is the sum squared error across all training samples that lie inside the rectangle. Sum, y, p, here, y is the output of the training sample, and p is the estimated output for the rectangle. The Gini index function is used for classification, and it indicates how pure the leaf nodes are. The formula for this is g equals sum, pk asterisk, 1, pk. Here, g is the Gini index, pk is the proportion of training instances with class k in the rectangle. Stopping criterion. As it works its way down the tree with the training data, the recursive binary splitting method described above must know when to stop splitting. The most frequent halting method is to utilize a minimum amount of training data allocated to each leaf node. If the count is less than a certain threshold, the split is rejected and the node is considered the last leaf node. The number of training members is adjusted according to the dataset. It specifies how exact the tree will be to the training data. Suggested blog, tree pruning. A decision tree's complexity is defined as the number of splits in the tree. Trees with fewer branches are recommended. They are simple to grasp and less prone to cluster the working through each leaf node in the tree and evaluating the effect of deleting it using a holdout test set is the quickest and simplest pruning approach. Only leaf nodes are eliminated if the total cost function for the complete test set decreases. When no additional improvements can be achieved, then no more nodes should be removed. More advanced pruning approaches, such as cost complexity pruning, also known as weakest link pruning, can be applied, in which a learning parameter, alpha, is used to determine whether nodes can be eliminated depending on the size of the subtree. Data preparation for cart algorithm. No special data preparation is required for the cart algorithm. Also read machine learning models. Advantages of cart algorithm. The cart algorithm is non-parametric, thus it does not depend on information from a certain sort of distribution. The cart algorithm combines both testings with a test data set and cross-validation to more precisely measure the goodness of cart allows one to utilize the same variables many times in various regions of the tree. This skill is capable of revealing intricate interdependencies between groups of variable. Outliers in the input variables have no meaningful effect on cart. One can loosen halting restrictions to allow decision trees to overgrow and then trim the tree down to its ideal size. This method reduces the likelihood of missing essential structure in the data set by terminating too soon. To choose the input set of variables, cart can be used in combination with other prediction algorithm. Similar reading, clustering out. Conclusion. The cart algorithm is a subpart of random forest, which is one of the most powerful algorithms of machine learning. The cart algorithm is organized as a series of questions, the responses to which decide the following question if any. The ultimate outcome of these questions is a tree-like structure with terminal nodes when there are no more questions. This algorithm is widely used in making decision trees through classification and regression. Decision trees are widely used in data mining to create a model that predicts the value of a target based on the values of many input variables, or independent variables. Classification and regression trees, CART, algorithm. Machine learning, ML. Get this book problems on array for interviews and competitive program. Classification and regression trees, CART, is only a modern term for what are otherwise known as decision trees. Decision trees have been around for a very long time and are important for predictive modeling in machine learning. As the name suggests, these trees are used for classification and prediction problems. This is an introductionary post about the fundamentals of such decision trees that serve the basis for other modern classifiers such as random forest. These models are obtained by partitioning the data space and fitting a simple prediction model within each partition. This is done recursively. We can represent the partitioning graphically as a tree, hence they have withstood the test of time because of the following reasons. Very competitive with other methods. High efficiency. Classification. Here our focus is to learn a target function that can be used to predict the values of a discrete class attribute. This is a classification problem where we want to know if, given labeled training data, something falls into one class or another. Naturally, this falls into supervised learning. This includes applications such as approving loans, high risk or low risk, predicting the weather, sunny, rainy, or cloudy. Let us explore solving the classification problem using a decision tree an example problem. Generally, a classification problem can be described as follows. Data, a set of records, instances, that are described by *k attributes, a1, a2, ak. *a class, discrete set of labels. Goal, to learn a classification model from the data that can be used to predict the classes of new, future, or test instances. Note when our problem has two possible labels, this is called a binary classification problem. E.g., predicting if someone's tumor is benign or malignant. Our example problem is loan approval prediction, and this is also a binary classification problem, either yes or no. Each record is for one loan applicant at a famous bank. The attributes being considered are age, job status, do they own a house or not, and their credit rate. What is impurity? The key to building a decision tree is in step 2 above, selecting which attribute to branch off on. We want to choose the attribute that gives us the most information. This subject is called information theory. In our dataset we can see that a loan is always approved when the applicant owns their own house. This is very informative and certain, and is hence set as the root node of the alternative decision tree shown previous. Classifying a lot of future applicants will be easy. Selecting the age attribute is not as informative. There is a degree of uncertainty, or impurity. The person's age does not seem to affect the final class as much. Based on the above discussion, a subset of data is pure if all instances belong to the same class. Our objective is to reduce impurity or uncertainty in data as much as possible. The metric, or heuristic, used in CART to measure impurity is the Gini index, and we select the attributes with lower Gini indices first. Here is the algorithm. / CART algorithm. Input, dataset D. 1 tree equals. 2 min loss equals 0. 3 for all attribute K and D do. 3.1 loss equals Gini index, K, D. 3 point, if loss. Min loss equals loss. 3.2.2 tree equals K. For partition, until all partitions PROC rest. We need to first define the Gini index, which is used to find the information gained by selecting an attribute. The Gini index favors larger partitions and is calculated for I equals 1 to the n, number of attributes. Gini equals 1, sigma, pi, 2. Here, pi is the probability that a tuple in D belongs to the class Ci. Now, coming back to the example problem. We shall solve this in steps. Step 1, find Gini, D. In our case, Gini, D, equals 1, 9/15, 2. Step 2, find Ginic, D, for each attribute K. Ginic, D, equals sigma d / d asterisk Gini, D. For I equals 1 to n, where D is a partition of the dataset D. So, for the attribute owns _ house. Step 3, partition at minimum Gini index values. As stated above, we need the root node of the decision tree to have the lowest possible Gini index, and in our case that is the attribute owns. The next attribute is job _ status. This is how we ultimately arrive at this decision tree. And using this decision tree for our problem, we can see that the applicant does not own a house, and does not have a job. decision tree learning, supervised learning, unsupervised learning, online learning, batch learning, semi-supervised learning, self-supervised learning, reinforcement learning, classification, regression, clustering, dimension reduction, density estimation, anomaly detection, data cleaning, auto-ML, association rules, structured prediction, feature engineering, feature learning, learning to rank, grammar induction, decision trees, ensembles bagging boosting random forest, bagging, boosting, random forest, KNN, linear regression, naive Bayes, artificial neural networks, logistic regression, perceptron, relevance vector machine, RVM, support vector machine, SVM. Birch, Cure, hierarchical, k-means, fuzzy, expectation. In this formalism, a classification or regression decision tree is used as a predictive model to draw conclusions about a set of observations. Tree models where the target variable can take a discrete set of values are called classification trees. In these tree structures, leaves represent class labels and branches represent conjunctions of features that lead to those class labels. Decision trees where the target variable can take continuous values, typically real numbers, are called regression trees. More generally, the concept of regression tree can be extended to any kind of object equipped with pairwise dissimilarities such as categorical sequences 1. Decision trees are among the most popular machine learning algorithms given their intelligibility and simplicity too. In decision analysis, a decision tree can be used to visually and explicitly represent decisions and decision making. In data mining, a decision tree describes data, but the result, general edit. Decision tree learning is a method commonly used in data mining. 3. The goal is to create a model that predicts the value of a target variable based on several input variables. A decision tree is a simple representation for classifying examples. For this section, assume that all of the input features have finite discrete domains, and there is a single target feature called the classification. Each element of the domain of the classification is called a class. A decision tree or a classification tree is a tree in which each internal, non-leaf, node is labeled with an input feature. The arcs coming from a node labeled with an input feature are labeled with each of the possible values of the target feature, or the arc leads to a subordinate decision node on a different input feature. Each leaf of the tree is labeled with a class or a probability distribution over the classes, signifying that the dataset has been classified by the tree into either a specific class, or into a particular probability distribution, which, if the decision tree is well constructed, is skewed towards certain subsets of classes. A tree is built by splitting the source set, constituting the root node of the tree, into subsets which constitute the successor children. The splitting is based on a set of splitting rules based on classification features. For this process is repeated on each derived subset in a recursive manner called recursive partitioning. The recursion is completed when the subset at a node has all the same values of the target variable, or when splitting no longer adds value to the prediction. This process of top-down induction of decision trees, TDID, 5 is an example of a greedy algorithm, and it is by far the most common strategy for learning decision trees from data 6.
I hate when this happens. Okay, so I'm gonna just replace this one and then move on to the next one. Let's search on Google, I think. Oh, whatever. I think I'm gonna leave it like this. I'm gonna move on to the next one. Machine learning algorithms have been making waves in recent years, changing the way we approach problem solving, blah blah blah. However, despite the many advances made in this field, there are many challenges to overcome, particularly when it comes to the interpretation and implementation. I'm gonna change this. I don't like this kind of introductions. CatBoost. Thing is, I'm not really sure if it's based on gradient descent or not.
Machine learning is a wide range of algorithms that learn from data to make better decisions and predictions. It is used in all kinds of tasks, from music and shopping recommendations to image and voice recognition to weather prediction. We have developed an open source and new machine learning tool that provides top accuracy for the most common business cases for machine learning. The tool is called CatBoost.
CatBoost is based on gradient boosting, a machine learning technique that works great if you have data from different sources. For example, to predict weather, it's best to use a combination of historical data, weather models, radar measurements, and data from weather stations.
CatBoost is complementary to deep learning, and it's generally easier to use. While deep learning methods work very well for homogeneous data, especially sensor data, like images, video, sounds, or text, gradient boosting shines when one wants to quickly incorporate many diverse data sources. Gradient boosting also works well when there is not much training data, whereas deep learning requires lots of data. The two play well together, however. Gradient boosting can easily integrate deep learning models and combine its outputs with other signals. One of our tutorials shows how TensorFlow trained deep learning-based text representations can be used as input into CatBoost. At Yandex, we use CatBoost to combine deep learning models for image-related tasks with other signals to provide best results to our users.
Most machine learning tools work only with numerical data, like height, weight, temperature, and so on. They do not support non-numerical features, like color, red, white, or blue, or CT. Thus, in order to use the algorithm, you need to find a way to convert those to numbers, which can be non-trivial. CatBoost does it for you in an optimal and innovative way that yields best in pure results. Also, many ML tools require so-called parameter tuning. You need to run ML algorithm many times during different knobs, and you only get good results after many runs. CatBoost provides excellent results after the first run, and its parameters are straightforward.
At Yandex, we're lucky to have some of the best engineers and data scientists in the world. We've been using machine learning in all of our products for a very long time. CatBoost is a next-generation platform built from our experience with MatrixNet, a technology that has been the basis of the quality leap that distinguishes our core products. We have released several of our best technologies into open source in the past, and now we're very excited to share our ML expertise with the open source community. In open sourcing CatBoost, we want to give data scientists across the world access to easy-to-use, accurate tool that gets efficient insights into data and allows achieving best results. We also see a great opportunity to add value to existing tool chains. CatBoost is compatible with other open source machine learning frameworks like TensorFlow and Keras. CatBoost trained models can also be integrated into Apple's most recently released Core ML to ship models on all kinds of devices. And of course, data scientists can use it directly in Python and R, their favorite playgrounds.
We see a variety of usages for CatBoost in business. CatBoost has been applied to very different things. For example, it was applied to optimizing alloys in steelmaking, dramatically reducing the cost of production. But it is also applied to things that we all experience in our daily life. For instance, with our weather forecasting service that uses CatBoost, we developed a technology that helps people with minute-to-minute hyperlocal forecasts that allows planning for quick weather changes. It also can be applied for recommending music or videos where everybody's taste is different. Getting best recommendations requires understanding many factors: historical, contextual, and social.
We're excited to see how CatBoost will be used to improve many machine learning applications. We hope that CatBoost will empower data scientists working in all sorts of industries and define a new standard of excellence in machine learning.
Understanding CatBoost algorithm. One of the best boosting algorithm. Photo by Hannah Troop on Unsplash. In this quick tutorial, we are going to discuss origins of CatBoost. When to use CatBoost, which type of data, how to implement CatBoost on any dataset. CatBoost originated in a Russian company named Yandex. It is one of the latest boosting algorithms out there as it was made available in 2017. There were many boosting algorithms like XGBoost, like GBM etc., but none comes close to the CatBoost for several reasons. CatBoost means categorical boosting because it is designed to work on categorical data flawlessly. If you have categorical data in your dataset, here are some features of the CatBoost, which makes it stand apart from all the other boosting algorithm. High quality without parameter tuning. Categorical features support the fast and scalable GPU version. Improved accuracy by reducing overfitting. Works well with less data. For the reason mentioned above, CatBoost is beloved in recent Kaggle competitions. Now let's answer another question: when to use this amazing boosting. When to use the CatBoost algorithm. There are two types of data out there: heterogeneous data and homogeneous data. Heterogeneous data, it is any data with high variability of data types and formats. They can be ambiguous and low quality due to missing values, high data redundancy. Example, dataset to predict credit score. Homogeneous data, it is dataset made up of the things which are similar to each other, which means that the entire dataset is of same data type and form. Example, dataset of images, video, sound, text. CatBoost works well on heterogeneous data. So, if you have a dataset of images, text, or sound, it is probably a good idea to use neural networks, as neural networks are state-of-the-art for these types of homogeneous data. But, if you have a classification problem with heterogeneous data, then using CatBoost will be the safest thing to do because CatBoost is able to outperform the majority of the boosting algorithms in the first round. Implementing CatBoost. We are going to apply CatBoost on a human activity recognition dataset for multi-class classification. Human activity recognition dataset is UCI dataset. In this classification problem, we have to predict 6 activities like walking, walking upstairs, walking downstairs, sitting, standing, and laying, based on the data extracted by smartphones sensors like gyroscope and accelerometer. To solve this problem, after importing the dataset, I applied the pre-processing using standard scalar, and after that came the main part where we apply CatBoost classifier. Let's see the classifier code and understand every single line. So, first of all, we have to import the CatBoost classifier as shown in the first line of the code. After importing the CatBoost library, we will create our model. Now let's go through those parameters. Iterations. 1000 iterations means the CatBoost algorithm will run 1000 times to minimize the loss function. And here, as we are classifying multiple classes, we have to specify multi-class. In the case of binary classification, it is okay if we don't mention the loss function. The algorithm will understand and perform binary classification. Bootstrap underscore type. This parameter affects the regularization and speed of the algorithm aspects of choosing a split for a tree when building the tree structure. Here we have chosen Bayesian, but it is okay if we didn't specify this parameter. Eval underscore metric. And here, as we have to do multi-class classification, we have chosen multi-class as eval underscore metric, and when working with binary classification, we don't have to specify this parameter. Leaf estimation iterations. This parameter defines rules for calculating leaf values after selecting the tree structure. We have taken 100, but it is also okay to not specify this parameter. Random strength. It specifies how random do we want our gradient boosting trees to be from each other. It is okay if we didn't specify. Depth. How deep do we want our tree to be? I have specified 7 because it gave me the highest accuracy, but it is okay not to specify it and let the CatBoost algorithm use its default value. L2 leaf regularization. To specify the L2 regularization value, we have taken 5, but it's not mandatory. Learning rate. It is very important, but generally default CatBoost learning rate of 0.03 also works. Bagging temperature defines the settings of the Bayesian bootstrap. It is used by default in classification and regression modes. Use the Bayesian bootstrap to assign random weights to object. Not mandatory to specify. Task type. It is very much recommended to use CatBoost algorithm with GPU only because with CPU CatBoost algorithm becomes quite slow. After changing the parameters and finding the best parameter, we will fit the model and predict the output. It is very easy to work with, and CatBoost only needs several parameters to tune. For example, if you are tuning depth, L2 underscore regularization, bagging underscore temperature, random underscore strength. Then you will be able to easily get very good performance compared to other boosting algorithm. In the CatBoost, you can run the model with just specifying the dataset type, binary or multi-class classification, and still you will be able to get a very good score without any overfit. So, this is how this algorithm works. I am providing some links in the reference through which you will be able to learn about this CatBoost algorithm. https://github.com/original-neat/human_activity_recognition_using_smartphone/blob/master/catboosting.py. https://catboost.ai. More from CatBoost, an in-depth guide Python API. What is CatBoost? CatBoost is an open source machine learning library that provides a fast and reliable implementation of gradient boosting on decision trees algorithm. Gradient boosted decision trees. Gradient boosted trees is a type of gradient booting machine's algorithm where all estimators of ensemble are decision trees. It combines predictions of these weak tree learners to predict final out. It can be used for classification, regression, ranking, and other machine learning tasks. CatBoost is developed by Yandex researchers and developers. It's used by various companies for tasks like search, recommendation systems, personal assistants, self-driving cars, weather prediction, etc. Why use CatBoost over other Python gradient boosting libraries? CatBoost provided support for handling categorical and text features of the data without the developer needing to handle them separate. CatBoost also provides support for grid search and randomized search, which lets us try out a list of values for parameters to find the best combination of parameters that gives the best result. CatBoost algorithm gives quite a good accuracy with default parameter settings. Apart from this, CatBoost also provides support for running the training process on GPU. It even lets us run the training process on multiple GPUs with simple configurations. CatBoost provides API in Python and R. What can you learn from this article? As a part of this tutorial, we have explained how to use Python library CatBoost to solve machine learning tasks, classification and regression. We have explained majority of CatBoost API with simple and easy to understand example. Apart from training models and making predictions, we have explained concepts like hyperparameters tuning, cross-validation, saving and loading model, recovering from interrupted training, early stopping to avoid overfitting, creating custom loss function, creating a custom evaluation metric, etc. All our examples are trained on toy datasets, structured, tabular, available from scikit-learn to keep things simple and easy to grasp. One of our sections at last also explains how to use CatBoost with text dataset. Tutorial is designed to get individuals started with using CatBoost and learn end-to-end Python API of CatBoost. Which other Python libraries provides implementation of gradient boosted trees? XGBoost, Light GBM, Scikit, how to install pip install ucat, conda install cat. Below, we have listed important sections of tutorial to give an overview of the material covered. We know that the list below is big, but you can skip some sections of tutorial which has a theory or repeat example of some concept. 1. Load datasets. We'll be using the below mentioned 3 different datasets which are available from scikit-learn as a part of this tutorial for explanation purposes. Boston housing dataset. It's a regression problem dataset which has information about the various attribute of houses in Boston and their price in dollars. This will be used for regression tasks. Breast cancer dataset. It's a classification dataset which has information about 2 different types of tumor. It'll be used for explaining binary classification task. 2 CatBoost models at high level API. CatBoost provides 3 different estimators to perform classification and regression tasks. CatBoost, it's a universal estimator which can handle both classification and regression datasets with setting. CatBoost Regressor, it is an estimator with scikit-learn-like API designed to work with regression datasets. CatBoost Classifier, it is an estimator with scikit-learn-like API designed to work with classification dataset. 3 CatBoost, regression example. The simplest way to train a model in CatBoost is by initializing the CatBoost estimator. The CatBoost constructor accepts only one parameter named params, which is a dictionary of parameters to be used to create an estimate. It has one main parameter named loss underscore function. Based on the value of this parameter, it determines whether the task is regression or classification. We can create a CatBoost estimator without passing any parameter, and it'll create an estimator with loss function as root mean squared error, which is used for regression task. All the parameters have some defined default values which we'll list down at the end of this section. By default, the CatBoost estimator trains for 1000 iterations, creating 1000 trees. It's an alias to the n underscore estimators parameter, which limits the number of trees. 3.1 Train simple CatBoost model, make predictions, and evaluate performance. Below we have created our first CatBoost estimator using the RMSE loss function. We have passed an iteration value of 100 to train it for 100 iteration. The verbose value of 10 will print results at every 10 iterations. The training process will create an ensemble of 100 trees. In the next cell, we have divided the Boston housing dataset into the train. We are now training our gradient boosting estimator created from previous steps by calling the fit method on it, passing it train data and labels. The fit method accepts many other parameters which we'll explain as we go ahead with the tutorial. We have then called the set underscore feature underscore names method, which can be used to set feature names for each column of data. The CatBoost estimator provides the method predict, which accepts feature. We'll now list down a list of important attributes and methods of the CatBoost estimator. Please make a note that this is not a list of all possible attributes and methods. There are many more methods which we'll cover later as well. Attributes. Best underscore score underscore. It returns the best score of the model. Classes underscore. It returns list of classes for classification problem. Feature underscore names underscore. It returns list of feature names. Feature underscore importances underscore. It returns the importance of each feature per algorithm. Learning underscore rate underscore. It returns the learning rate of the algorithm. Random underscore seed underscore. It returns a random seed from which initial model weights were assigned. Tree underscore count underscore. It returns the number of trees in the ensemble. N underscore features underscore n underscore. It returns the number of features used to train the model. Evals underscore result. It returns dictionary of evaluation. If we have provided an evaluation set, then evaluation results for it will be included. Methods. Get underscore best underscore score. It returns best score of the estimator. CatBoost, ML gradient boosting is an ensemble machine learning algorithm and typically used for solving classification and regression problems. It is easy to use and works well with heterogeneous data and even relatively small data. It essentially creates a strong learner from an ensemble of many weak learners. CatBoost or categorical boosting is an open source boosting library developed by Yandex. In addition to regression and classification, CatBoost can be used in ranking, recommendation systems, forecasting, and even personal assistance. Now, gradient boosting takes an additive form where it iteratively builds a sequence of approximations in a greedy manner, given a loss function. Here we would like to emphasize that the loss function has 2 input values, the ith expected output value e, and the tth function ft that estimates e. Assuming we have constructed function ft, we can improve our estimates of e by finding another function, whereas a step size in function is a base predictor chosen from a family of functions h in order to minimize the expected loss. That is, the minimization is approached by using Taylor approximation or the negative gradients, such that CatBoost makes refinements to this gradient boosting technique. Let there be a dataset D with n samples. Each sample has m set of features in a vector x, and a real valued target, y handling categorical features. Often datasets contain categorical features, and there are various techniques to handle categorical features in boosted trees. Unlike other gradient boosting algorithms, require numeric data, CatBoost automatically handles categorical features. One of the most common techniques for handling categorical data is one-hot encoding, but it becomes infeasible with many features. To tackle this, features are grouped in categories by target statistics. Estimate target value for each category. Target statistics can be calculated in different ways: greedy, hold out, leave one out, and or. CatBoost uses ordered target statistics. The greedy approach takes an average of the target for a category group, but it suffers from target leakage as the target value is being used to calculate a representation for the categorical variables, and then using those features for prediction is calculated using target. The holdout method tries to reduce this by partitioning the training dataset, but this significantly reduces the effective use of training data. Leave one out excludes the target sample but is not very effective. Ordered target statistics are inspired by online learning algorithms which get the training examples sequentially in time. It introduces artificial time, that is, a random permutation of the training example. It will only rely on the training examples encountered in its past. Samples occurred before that particular sample in the artificial time, thereby avoiding target leakage. Mathematically, the target estimate of the ith categorical variable of the kth element of D can be represented as the indicator function takes the value 1 when the ith component of CatBoost's input vector xj is. Here we use k as in the kth element according to the order we put on D with the random permutation, and I takes on the integer values 1 through k1. The parameters a and p, prior, save the equation from underflow. The if condition ensures the exclusion of the value of yk in the computation of values for 11 when encoding the value. This technique also ensures the use all the available past for each example to compute its target statistics and thereby encoding the categorical variable. Ordered boosting. Gradient boosting algorithms often have a tendency to overfit. Since ensembles work iteratively building upon the base learners over the same dataset, it affects the generalization capability of the model. When we use ordered target statistics to encode categorical variables, the partial derivatives, gradients, of the loss function L with respect to the function ft1 is also a random variable because we use the random permutation to choose the elements of dk to encode categorical variables that influence the value of ft1. Therefore, the distribution of gradients can be shifted under the condition that we calculated with a particular encoding for. This conditional shift leads to bias in the estimate we make for ht, and that negatively impacts the metrics we obtain when evaluating of ft1 on data. We did not use a training time. This impact on ft1 is referred to as its generalization capability and the problem is called a prediction shift. CatBoost introduces ordered boosting to avoid this problem. In ordered boosting, a random permutation of the training examples is performed and n different supporting models maintained. If model trained using only the first I samples in the permutation, and at each step residual/error is obtained by using previous model residual, but this is not feasible as data is finite and the memory requirement for maintaining different models would be too high. So CatBoost uses a variant for practical purposes. In this variant, one tree structure, sequence of splitting features, is shared by all the models. That is, CatBoost uses the same DK that determined the ordered target statistics as the data for determining the structure or fitting the decision tree HT, and uses the complete dataset D as the data for evaluating whether HT is the decision tree that minimizes the expected loss. It uses multiple permutations to compute a number of sets of residual values that it can use to find H, to obtain FT1, and maintain the guarantee that none of the values of is used to compute the values of the gradient, thereby reducing variance in the estimates of the gradients, rate of change of the loss function, and avoiding prediction shift. CatBoost advantages. CatBoost implements oblivious decision trees, binary tree in which same features are used to make left and right split for each level of the tree, thereby restricting the features split per level to 1, which help in decreasing prediction time. It handles categorical features effectively by ordered target statistics. It is easy to use with packages in R and Python. It has effective usage with default parameters, thereby reducing the time needed for parameter tuning. Cross-validated is a question and answer site for people interested in statistics, machine learning, data analysis, data mining, and data visualization. Cross-validated is a question and answer site for people. It only takes a minute to sign up. Sign up to join this community. The best answers are voted. How do ordered target statistics work for CatBoost? This question follows closely this paper. I'm trying to fully understand how ordered target statistics, TS, for CatBoost, work. E.g. the CatBoost algorithm uses this method to group categorical features through estimation of numerical values /het x underscore k caret I /approximate /math b /left y /mid x. Since this estimate can be noisy for low frequency categories, one can smooth it by some prior p so that /het x underscore k caret I equals /frac /sum underscore j equals 1 caret. Now, one uses the ordering principle which translates to me to order the whole dataset /mathcal d or some subsets of the dataset /mathcal d underscore k /mathcal d underscore k given some ordering function. I anticipate that the ordering function in the CatBoost algorithm is the artificial time which they define as a random permutation /sigma of the training example. Then, for each example they use all the available history. What is meant by history in this method? My best guess would be the following. In each step a random permutation is applied to /mathcal d. Afterwards /mathcal d is split into training and test examples. Then the test examples were expanded with all the training examples of the past step. 1 answer. 1. CatBoost in order to calculate the ordered target statistics defines various permutations of the training. Now at each step of the gradient boosting it chooses one of the permutation at random in order to calculate ordered TS. Now the history refers the sample that appears. Now let's look at the random sample. CatBoost in order to calculate the ordered target statistics defines various permutations of the training data. Now at each step of the gradient boosting it chooses one of the permutation at random in order to calculate ordered TS. Now the history refers the sample that appears before. Now let's look at the random sample from permutation below. For row ID 9, history comprises of row ID 2, but not row ID 3 as in this permutation it occurs after row ID. Your answer. Post your answer. By clicking post your answer, you agree to our terms of service, privacy policy, and cookie policy.
And this one, I think I'm gonna leave it like this. And it's very simple here because it's not looking like this example doesn't show the source code, so or the implementation directly from mathematics. That's when it gets complicated. But I don't think I'm gonna dive deep into this.
CatBoost, unbiased boosting with categorical features. 1 Introduction. Gradient boosting is a powerful machine learning technique that achieves state-of-the-art results in a variety of practical tasks. For many years, it has remained the primary method for learning problems with heterogeneous features, noisy data, and complex dependencies. Web search, recommendation system. Gradient boosting is essentially a process of constructing an ensemble predictor by performing gradient descent in a functional space. It is backed by solid theoretical results that explain how strong predictors can be built by iteratively combining weaker models, based predictors, in a greedy manner. 17. We show in this paper that all existing implementations of gradient boosting face the following statistical issue. A prediction model F obtained after several steps of boosting relies on the targets of all training examples. We demonstrate that this actually leads to a shift of the distribution of f, xk for a training example xk from the distribution of f, x for a test example x. This finally leads to a prediction shift of the learned model. We identify this problem as a special kind of target leakage in section 4. Further, there is a similar issue in standard algorithms of preprocessing categorical features. One of the most effective ways 25 to use them in gradient boosting is converting categories to their target statistics. A target statistic is a simple statistical model itself, and it can also cause target leakage in a prediction shift. We analyze this in section 3. In this paper, we propose ordering principle to solve both problems. Relying on it, we derive ordered boosting, a modification of standard gradient boosting algorithm, which avoids target leakage, section 4, and a new algorithm for processing categorical features, section 3. Their combination is implemented as an open source library, one called CatBoost, for categorical boosting. 2 Background. Assume we observe a data set of examples D equals xk, yk, k equals 1n, where xk equals x1k, xmk is a random vector of m features and yk set membership symbol r is a target, which can be either binary or a numerical response. Examples, xk, yk, are independent and identically distributed according to some unknown distribution p. The goal of a learning task is to train a function f, rm rightward arrow r which minimizes the expected loss L, f, equals L, y, f, x. Here L is a smooth loss function and x, y is a test example sampled from p independently of the training set D. A gradient boosting procedure 12 builds iteratively a sequence of approximations ft, rm rightward arrow r, t equals 0, 1. In a greedy fashion. Namely, ft is obtained from the previous approximation ft1 in an additive manner, ft equals ft1 plus alpha ht, where alpha is a step size in function ht, rm rightward arrow r, a base predictor, is chosen from a family of functions h in order to minimize the expected loss. ht equals argmin. H set membership symbol h. L, ft1 plus h, equals argmin. H set membership symbol h. L, y, ft1, x, plus h, x. 1. The minimization problem is usually approached by the Newton method using a second order approximation of L, ft1 plus ht, at ft1 or by taking a negative gradient step. Both methods are kinds of functional gradient descent 10, 24. In particular, the gradient step ht is chosen in such a way that ht, x, approximates gt, x, y, where gt, x, y, equals L, ys, s. S equals, CatBoost is an implementation of gradient boosting, which uses binary decision trees as base predictors. A decision tree 4, 10, 27 is a model built by a recursive partition of the feature space Rm into several disjoint regions, tree nodes, according to the values of some splitting attributes A. Attributes are usually binary variables that identify that some feature xk exceeds some threshold t, that is, a equals 1 xkt, where xk is either numerical or binary feature. In the latter case t equals 0.5.2. Each final region, leaf of the tree, is assigned to a value, which is an estimate of the response y in the region for the regression task or the predicted class label in the, where rj are the disjoint regions corresponding to the leaves of the tree. 3 Categorical features. 3.1 Related work on categorical features. A categorical feature is one with a discrete set of values called categories that are not comparable to each other. One popular technique for dealing with categorical features in boosted trees is one-hot encoding 7, 25, i.e., for each category, adding a new binary feature indicating it. However, in the case of high cardinality features, like, example, user ID, feature, such technique leads to an infeasibly large number of new features. To address this issue, one can group categories into a limited number of clusters and then apply one-hot encoding. A popular method is to group categories by target statistics, TS, that estimate expected target value in each category. Michibarica 25 proposed to consider TS as a new numerical feature instead. Importantly, among all possible partitions of 2 alternatively, non-binary splits can be used. Example, a region can be split according to all values of a categorical feature. However, such splits, compared to binary ones, would lead to either shallow trees, unable to capture complex dependencies, or to very complex trees with exponential number of terminal nodes, having weaker target statistics in each of them. According to 4, the tree complexity has a crucial effect on the accuracy of the model and less complex trees are less prone to overfitting. 3 In a regression task, splitting attributes and leaf values are usually chosen by the least squares criterion. Note that, in gradient boosting, a tree is constructed to approximate the negative gradient, see equation, 2, so it solves a regression problem. Categories into 2 sets, an optimal split on the training data in terms of log loss, Gini index, MSE can be found among thresholds for the numerical TS feature 4, section 4.2.211, section 9.2.4. In Light GBM 20, categorical features are converted to gradient statistics at each step of gradient boosting. Though providing important information for building a tree, this approach can dramatically increase computation time, since it calculates statistics for each categorical value at each step, and 2, memory consumption to store which category belongs to which node for each split based on a categorical feature. To overcome this issue, Light GBM groups tail categories into one cluster 21 and thus loses part of information. Besides, the authors claim that it is still better to convert categorical features with high cardinality to numerical features 19. Note that TS features require calculating and storing only one number per one category. Thus, using TS as new numerical features seems to be the most efficient method of handling categorical features with minimum information loss. TS are widely used, example in the click prediction task, click-through rates, 1, 15, 18, 22, where such categorical features as user, region, ad, publisher play a crucial role. We further focus on ways to calculate TS and leave one-hot encoding and gradient statistics out of the scope of the current paper. At the same time, we believe that the ordering principle proposed in this paper is also effective for gradient statistics. 3.2 Target statistics. As discussed in section 3.1, an effective and efficient way to deal with a categorical feature I is to substitute the categories of KTH training example with one numeric feature equal to some target statistic, TS, ZIC. Commonly, it estimates the expected target Y conditioned by the category. ZIC Y11 equals ZIC. Greedy TS a straightforward approach is to estimate Y11 equals ZIC as the average value of Y over the training examples with the same category ZIC 25. This estimate is noisy for low-frequency categories, and one usually smooths it by some prior P. ZIC equals sigma n. J equals 1. A common setting for P is the average target value in the dataset 25. The problem of such greedy approach is target leakage. Feature ZIC is computed using YK, the target of XK. This leads to a conditional shift 30. The distribution of 11y differs for training and test examples. The following extreme example illustrates how dramatically this may affect the generalization error of the learned model. Assume ith feature is categorical, all its values are unique, and for each category A, we have p, y equals 1, 11 equals A, equals 0.5 for a classification task. Then, in the training dataset, zik equals yk plus ap1 plus a, so it is sufficient to make only one split with threshold t equals 0.5 plus ap1 plus a to perfectly classify all training examples. However, for all test examples, the value of the greedy TS is p, and the obtained model predicts 0 for all of them if p. To this end, we formulate the following desired property for TS. P1e, 11y equals v, equals e, zik yk equals v, where xk, yk, is the kth training example. In our example above, e, zik yk, equals yk plus ap1 plus a and e, 11y, equals p are different. There are several ways to avoid this conditional shift. Their general idea is to compute the TS for xk on a subset of examples dk proper subset symbol d backslash xk excluding xk. Zik equals sigma. xj set membership symbol dk. 1 zik equals zik yj plus ap sigma. xj set membership symbol dk. 1 zik equals zik plus a. 5. Hold out TS one way is to partition the training dataset into two parts d equals d0, t, d1, and use dk equals d0 for calculating the TS according to 5 and d1. For training, example applied in 8 for CRIDEO dataset. Though such holdout TS satisfies P1, this approach significantly reduces the amount of data used both for training the model and calculating the TS. So, it violates the following desired property. P2 effective usage. Building a tree in CatBoost. Base predictors are oblivious decision trees 9, 14 also called decision tables 20. At the start, CatBoost generates S+1 independent random permutations of the training dataset. The permutations sigma 1, sigma s are used for evaluation of splits that define tree structures, i.e., the internal nodes, while sigma 0 serves for choosing the leaf values bj of the obtained trees. See equation 3. For examples with short history in a given permutation, both TS and predictions used by ordered boosting, m sigma, I, 1, 11, in algorithm 1, have a high variance. Therefore, using only one permutation may increase the variance of the final model predictions, while several permutations allow us to reduce this effect in a way we further describe. The advantage of several permutations is confirmed by our experiments in section 6. Building a tree in CatBoost. Base predictors are oblivious decision trees 9, 14 also called decision tables 23. Term oblivious means that the same splitting criterion is used across an entire level of the tree. Such trees are balanced, less prone to overfitting, and allow speeding up execution at testing time significantly. The procedure of building a tree in CatBoost is described in algorithm 2. In the ordered boosting mode, during the learning process, we maintain the supporting models MRJ, where MRJ, I, is the current prediction for the ith example based on the first j examples in the permutation sigma r. At each iteration t of the algorithm, we sample a random permutation sigma r from sigma 1, sigma s, and construct a tree tt on the basis of it. First, for categorical features, all ts are computed according to this permutation. Second, the permutation affects the tree learning procedure. Namely, based on MRJ, I, we compute the corresponding gradients grad j, I, equals L, ES, S. S equals MRJ, I. Then, while constructing a tree, we approximate the gradient g in terms of the cosine similarity cos, where, for each example I, we take the gradient grad or sigma, I, 1, I. It is based only on the previous examples in sigma r. At the candidate splits evaluation step, the leaf value, I, for example I is obtained individually by averaging the gradients grad or sigma r, I, one of the preceding examples p lying in the same leaf leafer, I, the example I belongs to. Note that leafer, I, depends on the chosen permutation sigma r, because sigma r can influence the values of ordered TS for example I. When the tree structure TT, i.e., the sequence of splitting attributes, is built, we use it to boost all the models MRJ. Let us stress that one common tree structure TT is used for all the models, but this tree is added to different MRJ with different sets of leaf values depending on R and J, as described in algorithm 2. The plain boosting mode works similarly to a standard GBDT procedure, but, if categorical features are present, it maintains S supporting models MR corresponding to TS based on sigma 1. Sigma S. Choosing leaf values given all the trees constructed, the leaf values of the final model F are calculated by the standard gradient boosting procedure equally for both modes. Training examples I are matched to leaves leaf 0, I, i.e., we use permutation sigma 0 to calculate TS here. When the final model F is applied to a new example at testing time, we use TS calculated on the whole training data according to section 3.2. Complexity in our practical implementation, we use one important trick, which significantly reduces the computational complexity of the algorithm. Namely, in the ordered mode, instead of O, SN2, values MRJ, I, we store and update only the values MRJ, I, equals MR2J, I, for J equals 1, log 2 any and all I with sigma R, I, less than or equal to 2J plus 1, what reduces the number of maintained supporting predictions to O, SN. See Appendix B for the pseudocode of this modification of algorithm 2. In Table 1, we present the computational complexity of different components of both CatBoost modes for one iteration. See Appendix C.1 for the proof. Here NTST is the number of TS to be calculated at the iteration T and C is the set of candidate splits to be considered at the given iteration. It follows that our implementation of ordered boosting with decision trees has the same asymptotic complexity as the standard GBDT with ordered TS. In comparison with other types of TS, section 3.2, ordered TS slow down by S times the procedure's calc gradient, updating supporting models M, and computation of TS. Feature combinations. Another important detail of CatBoost is using combinations of categorical features as additional categorical features which capture high-order dependencies like joint information of user ID and add topic in the task of bad click prediction. The number of possible combinations grows exponentially with the number of categorical features in the dataset, and it is infeasible to process all of them. CatBoost constructs combinations in a greedy way. Namely, for each split of a tree, CatBoost combines, concatenates, all categorical features, and their combinations, already used for previous splits in the current tree with all categorical features in the dataset. Combinations are converted to TS on the fly. Other important details. Finally, let us discuss two options of the CatBoost algorithm not covered above. The first one is subsampling of the dataset at each iteration of boosting procedure, as proposed by Friedman 13. We claimed earlier in section 4.1 that this approach alone cannot fully avoid the problem of prediction shift. However, since it has proved effective, we implemented it in both modes of CatBoost as a Bayesian bootstrap procedure. Specifically, before training a tree according to algorithm 2, we assign a weight wi equals ATI to each example I, where ATI are generated according to the Bayesian bootstrap procedure, C28, section 2. These weights are used as multipliers for gradients grad I and grad j I when we calculate I and the components of the vector g to define loss TC. The second option deals with first several examples in a permutation. For examples I with small values sigma r I, the variance of grad or sigma r I 1 I can be high. Therefore, we discard I from the beginning of the permutation when we calculate loss TC in algorithm 2. Particularly, we eliminate the corresponding components of vectors g and when calculating the cosine similarity between them. 6 experiments. Comparison with baselines. We compare our algorithm with the most popular open source libraries XGBoost and LightGBM on several well-known machine learning tasks. The detailed description of the
And I think I'm gonna leave it. I'm gonna leave this one like this. It's not good, but like it's true basic, but whatever. Just gonna do as many of them as possible, as fast as possible. And then I think I'll spend more time on the articles about blockchain once I go back and I finish reviewing all these algorithm articles. Then I take more time on the other ones. These ones I think I'm just gonna review and then pass there. I'm gonna go grab something to eat and then I will watch these videos here from True Blue, One Brown about linear algebra while I eat, and then after that I think I'm gonna meditate for 15 minutes and then I'll go back to reviewing these articles. I'm gonna try to do like 5 more or 4 more maybe. I think I'm gonna try to finish all of them today, the 3 ones, but I think I'm gonna do some of them off stream, depending on how long it takes for me to review each one. So I'll be right back.
completely described by where the basis vectors go. But now, there are three standard basis vectors that we typically use: the unit vector in the x direction, I hat, the unit vector in the y direction, j hat, and a new guy, the unit vector in the z direction, called k hat. In fact, I think it's easier to think about these transformations by only following those basis vectors, since the full 3D grid representing all points can get kind of messy. By leaving a copy of the original axes in the background, we can think about the coordinates of where each of these three basis vectors lands. Record the coordinates of these three vectors as the columns of a 3x3 matrix. This gives a matrix that completely describes the transformation using only 9 numbers. As a simple example, consider the transformation that rotates space 90 degrees around the y-axis. So that would mean that it takes I hat to the coordinates 0, 0, negative 1 on the z-axis. It doesn't move j hat, so it stays at the coordinates 0, 1, 0. And then k hat moves over to the x-axis at 1, 0, 0. Those three sets of coordinates become the columns of a matrix that describes that rotation transformation. To see where a vector with coordinates x, y, z lands, the reasoning is almost identical to what it was for 2 dimensions. Each of those coordinates can be thought of as instructions for how to scale each basis vector so that they add together to get your vector. And the important part, just like the 2D case, is that this scaling and adding process works both before and after the transformation. So to see where your vector lands, you multiply those coordinates by the corresponding columns of the matrix, and then you add together the three results. Multiplying two matrices is also similar. Whenever you see two 3x3 matrices getting multiplied together, you should imagine first applying the transformation encoded by the right one, then applying the transformation encoded by the left one. It turns out that 3D matrix multiplication is actually pretty important for fields like computer graphics and robotics, since things like rotations in 3 dimensions can be pretty hard to describe, but they're easier to wrap your mind around if you can break them down as the composition of separate, easier to think about rotations. Performing this matrix multiplication numerically is, once again, pretty similar to the 2-dimensional case. In fact, a good way to test your understanding of the last video would be to try to reason through what specifically this matrix multiplication should look like, thinking closely about how it relates to the idea of applying two successive transformations in space. In the next video, I'll start getting into the determinant. Hello again. So moving forward, I'll be assuming that you have a visual understanding of linear transformations and how they're represented with matrices, the way that I've been talking about in the last few videos. If you think about a couple of these linear transformations, you might notice how some of them seem to stretch space out, while others squish it on in. One thing that turns out to be pretty useful for understanding one of these transformations is to measure exactly how much it stretches or squishes things. More specifically, to measure the factor by which the area of a given region increases or decreases. For example, look at the matrix with columns 3, 0, and 0, 2. It scales I hat by a factor of 3 and scales j hat by a factor of 2. Now, if we focus our attention on the 1 by 1 square whose bottom sits on I hat and whose left side sits on j hat, after the transformation, this turns into a 2 by 3 rectangle. Since this region started out with area 1 and ended up with area 6, we can say the linear transformation has scaled its area by a factor of 6. Compare that to a shear, whose matrix has columns 1, 0, and 1, 1, meaning I hat stays in place and j hat moves over to 1, 1. That same unit square determined by I hat and j hat gets slanted and turned into a parallelogram, but the area of that parallelogram is still 1, since its base and height each continue to have length 1. So even though this transformation smushes things about, it seems to leave areas unchanged, at least in the case of that one unit square. Actually though, if you know how much the area of that one single unit square changes, it can tell you how the area of any possible region in space changes. For starters, notice that whatever happens to one square in the grid has to happen to any other square in the grid, no matter the size. This follows from the fact that grid lines remain parallel and evenly spaced. Then, any shape that's not a grid square can be approximated by grid squares pretty well, with arbitrarily good approximations if you use small enough grid squares. So, since the areas of all those tiny grid squares are being scaled by some single amount, the area of the blob as a whole will also be scaled by that same single amount. This very special scaling factor, the factor by which a linear transformation changes any area, is called the determinant of that transformation. I'll show how to compute the determinant of a transformation using its matrix later on in this video, but understanding what it represents is, trust me, much more important than the computation. For example, the determinant of a transformation would be 3 if that transformation increases the area of a region by a factor of 3. The determinant of a transformation would be 1/2 if it squishes down all areas by a factor of 1/2. And the determinant of a 2D transformation is 0 if it squishes all the space onto a line, or even onto a single point, since then the area of any region would become 0. That last example will prove to be pretty important. It means that checking if the determinant of a given matrix is 0 will give a way of computing whether or not the transformation associated with that matrix squishes everything into a smaller dimension. You'll see in the next few videos why this is even a useful thing to think about, but for now I just want to lay down all of the visual intuition, which in and of itself is a beautiful thing to think about. Okay, I need to confess that what I said so far is not quite right. The full concept of the determinant allows for negative values, but what would the idea of scaling an area by a negative amount even mean? This has to do with the idea of orientation. For example, notice how this transformation gives the sensation of flipping space over. If you were thinking of 2D space as a sheet of paper, a transformation like that one seems to turn over that sheet onto the other side. Any transformations that do this are said to invert the orientation of space. Another way to think about it is in terms of I hat and j hat. Notice that in their starting positions, j hat is to the left of I hat. If, after a transformation, j hat is now on the right of I hat, the orientation of space has been inverted. Whenever this happens, whenever the orientation of space is inverted, the determinant will be negative. The absolute value of the determinant, though, still tells you the factor by which areas have been scaled. For example, the matrix with columns 1, 1, and 2, negative 1 encodes a transformation that has determinant, I'll just tell you, negative 3. And what this means is that space gets flipped over and areas are scaled by a factor of 3. So why would this idea of a negative area scaling factor be a natural way to describe orientation flipping? Think about the series of transformations you get by slowly letting I hat get closer and closer to j hat. As I hat gets closer, all of the areas in space are getting squished more and more, meaning the determinant approaches 0. Once I hat lines up perfectly with j hat, the determinant is 0. Then, if I hat continues the way that it was going, doesn't it kind of feel natural for the determinant to keep decreasing into the negative numbers? So that's the understanding of determinants in 2 dimensions. What do you think it should mean for 3 dimensions? It also tells you how much a transformation scales things, but this time it tells you how much volumes get scaled. Just as in 2 dimensions, where this is easiest to think about by focusing on one particular square with an area 1 and watching only what happens to it, in 3 dimensions, it helps to focus your attention on the specific 1 by 1 by 1 cube whose edges are resting on the basis vectors I hat, j hat, and k hat. After the transformation, that cube might get warped into some kind of slanty cube. This shape, by the way, has the best name ever, parallelepiped, a name that's made even more delightful when your professor has a nice thick Russian accent. Since this cube starts out with a volume of 1, and the determinant gives the factor by which any volume is scaled, you can think of the determinant simply as being the volume of that parallelepiped that the cube turns into. A determinant of 0 would mean that all of space is squished onto something with 0 volume, meaning either a flat plane, a line, or, in the most extreme case, onto a single point. Those of you who watched chapter 2 will recognize this as meaning that the columns of the matrix are linearly dependent. Can you see why? What about negative determinants? What does that mean for 3 dimensions? One way to describe orientation in 3D is with the right hand rule. Point the forefinger of your right hand in the direction of I hat, stick out your middle finger in the direction of j hat, and notice how when you point your thumb up, it's in the direction of k hat. If you can still do that after the transformation, orientation has not changed, and the determinant is positive. Otherwise, if after the transformation it only makes sense to do that with your left hand, orientation has been flipped, and the determinant is negative. So if you haven't seen it before, you're probably wondering by now, how do you actually compute the determinant? For a 2 by 2 matrix with entries a, b, c, d, the formula is a times d minus b times c. Here's part of an intuition for where this formula comes from. Let's say that the terms b and c both happen to be 0. Then the term a tells you how much I hat is stretched in the x direction, and the term d tells you how much j hat is stretched in the y direction. So, since those other terms are 0, it should make sense that a times d is the area of the rectangle that our favorite unit square turns into, kind of like the 3002 example from earlier. Even if only one of the are 0, you'll have a parallelogram with a base a and a height d, so the area should still be a times d. Loosely speaking, if both b and c are non-zero, then that b times c term tells you how much this parallelogram is stretched or squished in the diagonal direction. For those of you hungry for a more precise description of this b times c term, here's a helpful diagram if you'd like to pause and ponder. Now, if you feel like computing determinants by hand is something that you need to know, the only way to get it down is to just practice it with a few. There's really not that much I can say or animate that's going to drill into computation. This is all triply true for three-dimensional determinants. There is a formula, and if you feel like that's something you need to know, you should practice with a few matrices, or, go watch Sal Khan work through a few. Honestly, though, I don't think that those computations fall within the essence of linear algebra, but I definitely think that understanding what the determinant represents falls within that essence. Here's kind of a fun question to think about before the next video. If you multiply two matrices together, the determinant of the resulting matrix is the same as the product of the determinants of the original two matrices. If you tried to justify this with numbers, it would take a really long time, but see if you can explain why this makes sense in just one sentence. Next up, I'll be relating the idea of linear transformations covered so far to one of the areas where linear algebra is most useful, linear systems of equations. See you then. As you can probably tell by now, the bulk of this series is on understanding matrix and vector
Right, I think I'm gonna spend 1.5 hours more. Then I'll decide if I'll take a break or continue. The decision tree algorithm is a powerful and versatile tool for solving complex problems, making accurate predictions. It is widely used in various fields. In this article, we'll dive deep into the decision tree algorithm, exploring its concepts, working mechanisms, applications, and more. I think this is the one that I already read some stuff about in one of the articles.
Learn the pros and cons of using decision trees for data mining and knowledge discovery tasks. A decision tree is a non-parametric supervised learning algorithm, which is utilized for both classification and regression tasks. It has a hierarchical tree structure, which consists of a root node, branches, internal nodes, and leaf nodes. As you can see from the diagram above, a decision tree starts with a root node, which does not have any incoming branches. The outgoing branches from the root node then feed into the internal nodes, also known as decision nodes. Based on the available features, both node types conduct evaluations to form homogeneous subsets, which are denoted by leaf nodes, or terminal node. The leaf nodes represent all the possible outcomes within the dataset. As an example, let's imagine that you were trying to assess whether or not you should go surf. You may use the following decision rules to make a choice. This type of flowchart structure also creates an easy-to-digest representation of decision-making, allowing different groups across an organization to better understand why a decision was made. Decision tree learning employs a divide-and-conquer strategy by conducting a greedy search to identify the optimal split points within a tree. This process of splitting is then repeated in a top-down, recursive manner until all, or the majority of records have been classified under specific class label. Whether or not all data points are classified as homogeneous sets is largely dependent on the complexity of the decision tree. Smaller trees are more easily able to attain pure leaf nodes i.e. data points in a single class. However, as a tree grows in size, it becomes increasingly difficult to maintain this purity, and it usually results in too little data falling within a given subtree. When this occurs, it is known as data fragmentation, and it can often lead to overfitting. As a result, decision trees have preference for small trees, which is consistent with the principle of parsimony in Occam's razor. That is, entities should not be multiplied beyond necessity. Said differently, decision trees should add complexity only if necessary, as the simplest explanation is often the best. To reduce complexity and prevent overfitting, pruning is usually employed. This is a process which removes branches that split on features with low importance. The model's fit can then be evaluated through the process of cross-validation. Another way that decision trees can maintain their accuracy is by forming an ensemble via a random forest algorithm. This classifier predicts more accurate results, particularly when the individual trees are uncorrelated with each other. Hunt's algorithm, which was developed in the 1960s to model human learning in psychology, forms the foundation of many popular decision tree algorithms, such as the following. ID3. Ross Quinlan is credited within the development of ID3, which is shorthand for iterative dichotomy SIR3. This algorithm leverages entropy and information gain as metrics to evaluate candidate split. Some of Quinlan's research on this algorithm from 1986 can be found here. PDF, 1.4 megabytes. Link resides outside of IBM.com. C4.5. This algorithm is considered a later iteration of ID3, which was also developed by Quinlan. It can use information gain or gain ratios to evaluate split points within the decision trees. CART. The term CART is an abbreviation for classification and regression trees and was introduced by Leo Breen. This algorithm typically utilizes Gini impurity to identify the ideal attribute to split on. Gini impurity measures how often a randomly chosen attribute is misclassified. When evaluating using Gini impurity, a lower value is more ideal. How to choose the best attribute at each node. While there are multiple ways to select the best attribute at each node, two methods, information gain and Gini impurity, act as popular splitting criterion for decision tree model. They help to evaluate the quality of each test condition and how well it will be able to classify samples into a class. Entropy and information gain. It's difficult to explain information gain without first discussing entropy. Entropy is a concept that stems from information theory, which measures the impurity of the sample values. It is defined by the following formula, where S represents the data set that entropy is calculated. C represents the classes in set. SP, C, represents the proportion of data points that belong to class C to the number of total data points in set. Entropy values can fall between 0 and 1. If all samples in data set, S, belong to one class, then entropy will equal 0. If half of the samples are classified as one class and the other half are in another class, entropy will be at its highest at 1. In order to select the best feature to split on and find the optimal decision tree, the attribute with the smallest amount of entropy should be used. Information gain represents the difference in entropy before and after a split on a given attribute. The attribute with the highest information gain will produce the best split as it's doing the best job at classifying the training data according to its target classification. Information gain is usually represented with the following formula, where A represents a specific attribute or class label. Entropy, S, is the entropy of dataset. SV/S represents the proportion of the values in SV to the number of values in dataset. S entropy, SV, is the entropy of dataset, SV. Let's walk through an example to solidify these concepts. Imagine that we have the following arbitrary dataset. For this dataset, the entropy is 0.94. This can be calculated by finding the proportion of days where play tennis is yes, which is 9/14, and the proportion of days where play tennis is no, which is then these values can be plugged into the entropy formula above. Entropy, tennis, equals dash, 9/14, log 2, 9/14, 5/14, log 2. We can then compute the information gain for each of the attributes individually. For example, the information gain for the attribute, humidity would be the following. Gain, tennis, humidity, equals, as a recap. 7/14 represents the proportion of values where humidity equals high to the total number of humidity values. In this case, the number of values where humidity equals high is the same as the number of values where humidity equals normal. 0.985 is the entropy when humidity equals high. 0.59 is the entropy when humidity equals normal. Then, repeat the calculation for information gain for each attribute in the table above, and select the attribute with the highest information gain to be the first split point in the decision tree. In this case, Outlook produces the highest information gain. From there, the process is repeated for each subtree. Gini impurity. Gini impurity is the probability of incorrectly classifying random data point in the dataset if it were labeled based on the class distribution of the dataset. Similar to entropy, if set S is pure i.e. belonging to one class, then its impurity is 0. This is denoted by the following formula. Advantages and disadvantages of decision trees. While decision trees can be used in a variety of use cases, other algorithms typically outperform decision tree algorithms. That said, decision trees are particularly useful for data mining and knowledge discovery tasks. Let's explore the key benefits and challenges of utilizing decision trees more below. Easy to interpret. The Boolean logic and visual representations of decision trees make them easier to understand and consume. The hierarchical nature of a decision tree also makes it easy to see which attributes are most important, which isn't always clear with other algorithms, like neural network. Little to no data preparation required. Decision trees have a number of characteristics, which make it more flexible than other classifiers. It can handle various data types, discrete or continuous values, and continuous values can be converted into categorical values through the use of thresholds. Additionally, it can also handle values with missing values, which can be problematic for other classifiers, like naive Bayes. More flexible, decision trees can be leveraged for both classification and regression tasks, making it more flexible than some other algorithms. It's also insensitive to underlying relationships between attributes. This means that if two variables are highly correlated, the algorithm will only choose one of the features to split up. Prone to overfitting. Complex decision trees tend to overfit and do not generalize well to new data. This scenario can be avoided through the processes of pre-pruning or post-pruning. Pre-pruning halts tree growth when there is insufficient data, while post-pruning removes subtrees with inadequate data after tree construction. High variance estimators. Small variations within data can produce a very different decision tree. Bagging, or the averaging of estimates, can be a method of reducing variance of decision trees. However, this approach is limited as it can lead to highly correlated predictor. More costly, given that decision trees take a greedy search approach during construction. They can be more expensive to train compared to other algorithms. Not fully supported in scikit-learn. Scikit-learn is a popular machine learning library based in Python. While this library does have a decision tree module, decision tree classifier, link resides outside of IBM.com. The current implementation does not support categorical variable. IBM SPSS Modeler is a data mining tool that allows you to develop predictive models to deploy them into business operations. Designed around the industry standard CRISP DM model, IBM SPSS Modeler supports the entire data mining Decision tree algorithm overview explained. 1 overview. Decision tree analysis is a general, predictive modeling tool with applications spanning several different areas. In general, decision trees are constructed via an algorithmic approach that identifies ways to split a data set based on various conditions. It is one of the most widely used and practical methods for supervised learning. Decision trees are a non-parametric supervised learning method used for both classification and regression tasks. The goal is to create a model that predicts the value of a target variable by learning simple decision rules inferred from the data feature. The decision rules are generally in the form of if-then-else statements. The deeper the tree, the more complex the rules and fitter the model. Before we dive deep, let's get familiar with some of the terminologies. Instances refer to the vector of features or attributes that define the input space. Attribute, a quantity describing an instance. Concept, the function that maps input to output. Target concept, the function that we are trying to find, i.e., the actual answer. Hypothesis class, set of all the possible functions. Sample, a set of inputs paired with a label, which is the correct output, also known as the training set. Candidate concept, a concept which we think is the target concept. Testing set, similar to the training set and is used to test the candidate concept and determine its performance. Decision trees are simple to implement and equally easy to interpret. And decision trees are ideal for machine learning newcomers as well. Decision trees can be applied to both regression and classification problem, but the questions you should ask, and should know the answer to, are: what is a decision tree? How does it work? Why we have to use decision trees? What is the mathematics behind this algorithm? If you are unsure about even one of these questions, you've come to the right place. Decision tree is a robust machine learning algorithm that also serves as the building block for other widely used and complicated machine learning algorithms like random forest, XGBoost, AdaBoost, and LightGBM. You can imagine why it's essential to learn about this topic. Modern-day programming libraries have made using any machine learning algorithm easy, but this comes at the cost of hidden implementation, a must-know for fully understanding an algorithm. 3 terminologies. Let's look at the basic terminology used with decision trees. Root node, it represents the entire population or sample, and this further gets divided into 2 or more homogeneous set. Leaf/terminal node, nodes do not split is called leaf or terminal node. Decision node, when a subnode splits into further subnodes, then it is called a decision node. Branch/subtree, a subsection of the entire tree is called a branch or subtree. Parent and child node, a node, which is divided into subnodes, is called the parent node of subnodes, whereas subnodes are the child of the parent. Splitting, it is a process of dividing a node into 2 or more subnodes. Pruning, pruning is when we selectively remove branches from a tree. The goal is to remove unwanted branches, improve the tree's structure, and direct new, healthy growth. For what is a decision tree algorithm? A decision tree is a tree-like graph with nodes representing the place where we pick an attribute and ask a question, edges represent the answers to the question, and the leaves represent the actual output or class label. They are used in nonlinear decision-making with a simple linear decision surface. The decision tree algorithm belongs to the family of supervised learning algorithm. Unlike other supervised learning algorithms, the decision tree algorithm can solve regression and classification problems. The goal of using a decision tree is to create a training model that can use to predict the class or value of the target variable by learning simple decision rules inferred from prior data, training data. In decision trees, we start from the tree's root for predicting a class label for a record. We compare the values of the root attribute with the record's attribute. Based on the comparison, we follow the branch corresponding to that value and jump to the next node. 5. Why we have to use decision tree algorithm? Decision tree is considered one of the most useful machine learning algorithms since it can solve various problems. Here are a few reasons why you should use the decision tree. It is considered to be the most understandable machine learning algorithm, and it can be easily interpreted. It can be used for classification and regression problems. Unlike most machine learning algorithms, it works effectively with nonlinear data. Constructing a decision tree is a speedy process since it uses only one feature per node to split the data. Decision trees model data as a tree of hierarchical branches. They make branches until they reach leaves that represent predictions. Due to their branching structure, decision trees can easily model nonlinear relationship. 6. How does the decision tree algorithm work? In a decision tree, for predicting the class of the given dataset, the algorithm starts from the root node of the. This algorithm compares the values of the root attribute with the record, real dataset, attribute, and, based on the comparison, follows the branch and jumps to the next node. For the next node, the algorithm again compares the attribute value with the other subnodes and moves further. It continues the process until it reaches the leaf node of the. The complete algorithm can be better divided into the following steps. Step 1. Begin the tree with the root node, says S, which contains the complete dataset. Step 2. Find the best attribute in the dataset using attribute selection measure, ASM. Step 3. Divide the S into subsets that contains possible values for the best attribute. Step 4. Generate the decision tree node, which contains the best attribute. Step 5. Recursively make new decision trees using the subsets of the dataset created in step -3. Continue this process until a stage is reached where you cannot further classify the nodes and call the final node as a leaf node. Consider the following dataset. The tree for this dataset may look like this dash. We will use the attribute selection measure at each node to split the dataset to find the best tree. 7. Attribute selection measures. Information gain. Information gain is used as an attribute selection measure. Pick the attribute that has the highest information gain. Here, D, a given data partition. A, attribute. V. Suppose we partition the tuples in D on some attribute A having V distinct values. D is split into V partition or subsets, D1, D2. Dj, where Dj contains those tuples in D that have outcome Aj of A. Entropy. Entropy is a measure of the uncertainty associated with a random variable. As uncertainty and or randomness increases for a result set, so does the entropy. Values range from 0 to 1 to represent the entropy of information, where pi is the probability that a target feature takes. For example, considering the above entropy, D equals entropy, pi's underscore computer, equals dash, 9/14 log 2, 9/14, plus 5/14 log 2, 5/14, equals entropy, D, 5/14, entropy, Seuth, 4/14, entropy, Smidl underscore aged, 5/14, asterisk entropy, senior. Equals 0.940, 5/14, 0.347, 4/14, 0.0, 5/14, equals 0. Similarly, gain, income, D, equals 0.029, gain, Gini index. Gini index is a measure of impurity or purity used while creating a decision tree in the cart, classification and regression tree, algorithm. An attribute with a low Gini index should be preferred as compared to the high Gini index. Gini index can be calculated using the below formula. Let's calculate the Gini index for the credit underscore rating in the previous example. P, credit underscore rating, P, Gini equals, weighted Gini, credit underscore rating, equals, 814. Similarly, it can be calculated for others. 8 building a tree. To build a tree for the above example, we will start taking the tree considering the whole dataset as a root node to find whether someone buys a compute. Now, we will find the best attribute to split using the attribute selection measure, ASM. Here we are using the ID3 algorithm to build the tree. So we are going to calculate information gain using entropy, which is already calculated in the ASM sec. Information gain for the age attribute is highest, so we will split the dataset according to the age at the root node. After the splitting at root node tree will look like this. Recursively we will split all generated nodes till we reach the node where splitting is not possible. And in this way, we will generate our required tree. 9 advantages and disadvantages of decision tree. Trees are very easy to explain to people. They are even easier to explain than linear regression. Decision trees more closely mirror human decision making than make the regression and classification approach. Trees can be displayed graphically and easily interpreted even by a non-expert, especially small trees. Trees can easily handle qualitative predictors without the need to create dummy variable. The decision tree is considered to be a non-parametric method. This means that decision trees have no assumptions about the spatial distribution and the classifier structure. It can handle both numerical and categorical variables. Unfortunately, trees generally do not have the same level of predictive accuracy as some of the other regression and classification approaches. Additionally, trees can be very non-robust. In other words, a slight change in the data can cause a significant difference in the final estimated disadvantages. However, by aggregating many decision trees, using methods like bagging, random forests, and boosting, the predictive performance of trees can be substantially improved. 10 practical applications. Which product will be more profitable at launch in companies? Given the sales attributes such as market conditions, competition, price, availability of raw materials, demand, etc., a decision tree classifier can be used to determine which of the products would maximize the profits. Accurate sentiment analysis. Sentiment analysis is the decision tree algorithm. Introduction to decision tree algorithm. The decision tree algorithm is one of the popular supervised type machine learning algorithms that is used for. This algorithm generates the outcome as the optimized result based upon the tree structure with the conditions or rules. The decision tree algorithm associated with 3 major components as decision nodes, design links, and decision leaf. It operates with the splitting, pruning, and tree selection process. It supports both numerical and categorical data to construct the decision tree. Decision tree algorithms are efficient for large data set with less time complexity. This algorithm is mostly used in customer segmentation and marketing strategy implementation in the business. What is decision tree algorithm? Decision tree algorithm is a supervised machine learning algorithm where data is continuously divided at each row based on certain rules until the final outcome is generated. Let's take an example. Suppose you open a shopping mall and of course, you would want it to grow in business with time. So for that matter, you would require returning customers plus new customers in your. For this, you would prepare different business and marketing strategies such as sending emails to potential customers, create offers and deals, targeting new customers, etc. But how do we know who are the potential customers? In other words, how do we classify the category of the customers? Like some customers will visit once in a week and others would like to visit once or twice in a month, or some will visit in a quarter. So decision trees are one such classification algorithm that will classify the results into groups until no more similarity is left. In this way, the decision tree goes down in a tree structured form. The main components of a decision tree are decision nodes, which is where the data is split, or say, it is a place for the attribute. Decision link, which represents a root. Decision leaves, which are the final outcomes. Working of a decision tree algorithm. There are many steps that are involved in the working of a decision tree. 1. Splitting. It is the process of the partitioning of data into subset. Splitting can be done on various factors as shown below, i.e. on a gender basis, height basis, or based on class. 2. Pruning. It is the process of shortening the branches of the decision tree, hence limiting the tree depth. Pruning is also of 2 types. .bf underscore badge position absolute, right dash 2 px, top dash 12 px, width 90 px, span blg price underscore. Pre-pruning. Here, we stop growing the tree when we do not find any statistically significant association between the attributes and class at any particular node. Post-pruning. In order to post-prune, we must validate the performance of the test set model and then cut the branches that are a result of overfitting noise from the training. 3. Tree selection. The third step is the process of finding the smallest tree that fits the data. Example and illustration of constructing a decision. Let's say you want to play cricket on some particular day, for example Saturday. What are the factors that are involved which will decide if the play is going to happen or not? Clearly, the major factor is the climate. No other factor has that much probability as much climate is having for the play interruption. We have collected the data from the last 10 days, which is presented below. Let us now construct our decision tree based on the data that we have got. So we have divided the decision tree into 2 levels. The first one is based on the attribute weather, and the second row is based on humidity and wind. We can also set some threshold values if the features are continuous. What is entropy in decision tree algorithm? In simple words, entropy is the measure of how disordered your data is. While you might have heard this term in your mathematics or physics classes, it's the same here. The reason entropy is used in the decision tree is because the ultimate goal in the decision tree is to group similar data groups into similar classes, to tidy the data. Let us see the below image, where we have the initial data set, and we are required to apply a decision tree algorithm in order to group together the similar data points in one category. After the decision split, as we can clearly see, most of the red circles fall under one class while most of the blue crosses fall under another class. Hence a decision was to classify the attributes that could be based on various factors. Now, let us try to do some math over here. Let us say that we have got n sets of the item, and these items fall into 2 categories, and now in order to group the data based on labels, we introduce the ratio. The entropy of our set is given by the following equation. Let us check out the graph for the given equation. Above image, with p equals 0.5 and q equals 0. Advantages and disadvantages. Given below are the advantages and disadvantages mentioned. Advantages. A decision tree is simple to understand, and once it is understood, we can implement a decision tree on numerical as well as categorical data. Decision tree is proven to be a robust model with promising outcomes. They are also time efficient with large data. It requires less effort for the training of the data. Disadvantages. Instability. Only if the information is precise and accurate, the decision tree will deliver promising result. Even if there is a slight change in the input data, it can cause large changes in the tree. Complexity. If the dataset is huge with many columns and rows, it is a very complex task to design a decision tree with many branches.
Decision tree algorithms have been popular choice for supervised learning problems for many years. They work by recursively splitting the data into smaller subsets based on the values of the features until each subset is pure. Contains only data points belonging to one class. However, decision trees are prone to overfitting, which is why several methods have been proposed to make them more robust, such as bagging, random forest, and extra trees. We'll focus on extra trees, also known as extremely randomized trees, and see how it can be used for classification and regression problems. What are extra trees? Extra trees are an extension of random forests, which are an ensemble of decision trees. The key difference between the two is that while in random forests, the split points are chosen by selecting the best feature and threshold based on some criterion. In extra trees, the split points are selected at random. This randomization makes extra trees less prone to overfitting than decision trees or random forests, and also faster to train. For extra trees can be summarized as follows. For each tree in this ensemble, a random subset of the features is selected. For each split in the tree, a random threshold is chosen for one of the features in the selected subset. The split that results in the maximum reduction of impurity is chosen as the split point. The process is repeated recursively until a stopping criterion is met, such as maximum tree depth or a minimum number of samples in a leaf node. Randomization by selecting random features and thresholds, extra trees are less prone to overfitting and more robust to noisy data. It's pretty much a variation of the previous ones that I already looked into it. The only difference is that it uses randomization to guide the whole entropy thing when it's splitting the nodes. Fast training, since is very similar to some, like obviously it's different because it's a tree algorithm, but there is some randomization techniques when choosing weights, I think, and biases, or don't remember really well. I think it's batching techniques as well when you're building the models with linear regression and other forms of regression, I think, where you can randomize the different data points and you can also normalize or drop some of the nodes as well. There's some techniques like that. So it's kind of a similar thing where you have a bunch of different variations. In the same way, you can also have variations on the gradient descent method. So when it comes to trees, you also have a bunch of these variations, but the core fundamental, I think, is pretty much the same. You're building a tree of decisions, and then based on whatever method you choose for creating the decisions is gonna be optimized for different types of things. And then it's prone to overfitting because of this property of decisions based on the tree. So it's not hard to understand, I think. I think I'm gonna leave it like this and move on to the next one. I'm gonna read some stuff about it and then I'm gonna move on.
How extra trees classification and regression algorithm works. Extra trees, short for extremely randomized trees, is an ensemble supervised machine learning method that uses decision trees and is used by the train using AutoML. See decision trees classification and regression algorithm for information about how decision trees work. This method is similar to random forests but can be fast. The extra trees algorithm, like the random forests algorithm, creates many decision trees, but the sampling for each tree is random, without replacement. This creates a dataset for each tree, with unique samples. A specific number of features, from the total set of features, are also selected randomly for each tree. The most important and unique characteristic of extra trees is the random selection of a splitting value for a feature. Instead of calculating a locally optimal value using Gini or entropy to split the data, the algorithm randomly selects a split value. This makes the trees diversified and uncorrelated. Additional resource. How to develop an extra trees ensemble with Python. Tweet. Share. Last updated on April 27, 2021. Extra trees is an ensemble machine learning algorithm that combines the predictions from many decision trees. It is related to the widely used random forest algorithm. It can often achieve as good or better performance than the random forest algorithm, although it uses a simpler algorithm to construct the decision trees used as members of the ensemble. It is also easy to use given that it has few key hyperparameters and sensible heuristics for configuring these hyperparameters. In this tutorial, you will discover how to develop extra trees ensembles for classification and regression. After completing this tutorial, you will know extra trees ensemble is an ensemble of decision trees and is related to bagging and random forest. How to use the extra trees ensemble for classification and regression with scikit-learn. How to explore the effect of extra trees model hyperparameters on model performance. Kickstart your project with my new book Ensemble Learning Algorithms with Python, including step-by-step tutorials and the Python source code files for all example. Let's get started. How to develop an extra trees ensemble with Python photo by Nicholas Raymond. Some rights reserved. Tutorial overview. This tutorial is divided into 3 parts. They are extra trees algorithm, extra trees scikit-learn API, extra trees for classification, extra trees for regression, extra trees hyperparameters, explore number of trees, explore number of features, explore minimum samples per split, extra trees algorithm. Extremely randomized trees, or extra trees for short, is an ensemble machine learning algorithm. Specifically, it is an ensemble of decision trees and is related to other ensembles of decision trees algorithms such as bootstrap aggregation, bagging, and random forest. The extra trees algorithm works by creating a large number of unprint decision trees from the training dataset. Predictions are made by averaging the prediction of the decision trees in the case of regression or using majority voting in the case of classification. Regression, predictions made by averaging predictions from decision trees. Classification, predictions made by majority voting from decision trees. The predictions of the trees are aggregated to yield the final prediction by majority vote in classification problems and arithmetic average in regression problem. Extremely randomized trees, 2006. Unlike bagging and random forest that develop each decision tree from a bootstrap sample of the training dataset, the extra trees algorithm fits each decision tree on the whole training dataset. Like random forest, the extra trees algorithm will randomly sample the features at each split point of a decision tree. Unlike random forest, which uses a greedy algorithm to select an optimal split point, the extra trees algorithm selects a split point at random. The extra trees algorithm builds an ensemble of unprint decision or regression trees according to the classical top-down procedure. Its two main differences with other tree-based ensemble methods are that it splits nodes by choosing cut points fully at random and that it uses the whole learning sample, rather than a bootstrap replica, to grow the tree. Extremely randomized trees, 2006. As such, there are 3 main hyperparameters to tune in the algorithm. They are the number of decision trees in the ensemble, the number of input features to randomly select and consider for each split point, and the minimum number of samples required in a node to create a new split point. It has 2 parameters, k, the number of attributes randomly selected at each node, and min, the minimum sample size for splitting a node. We denote by m the number of trees of this ensemble. Extremely randomized trees, extra trees scikit-learn API. Extra trees ensembles can be implemented from scratch, although this can be challenging for beginners. The scikit-learn Python machine learning library provides an implementation of extra trees for machine learning. It is available in a recent version of the library. First, confirm that you are using a modern version of the library by running the following script. Hashtag check scikit-learn version. Import scikit-learn. Print, scikit-learn __ version __ 123. Hashtag check scikit-learn version import scikit-learn print, scikit-learn __ version __ Running the script will print your version of scikit-learn.
I'm just gonna move on to the next one. Not that interesting. Weighting boosting is a popular machine learning technique that has been widely adopted in recent years. The method is based on combining multiple simple models, like decision trees, to create a more powerful, unified model. This technique can lead to significant improvements in model accuracy, making it an excellent choice for many real-world problems. Gradient boosting is an ensemble method that combines multiple weak models to create a stronger, more accurate model. The method involves training multiple trees, typically decision trees, one at a time, and adding them to the final model in a way that minimizes the loss function. This iterative process continues until a stopping criterion is reached, such as maximum number of trees or a threshold for the improvement in model accuracy. At its core, gradient boosting works by using the output of one tree to train the next. After each tree is trained, the algorithm uses the residual of the previous tree's prediction to train the next tree. The residuals are the differences between the actual values and the predictions made by the previous tree. By focusing on the residuals, the algorithm can gradually improve the accuracy of the model by correcting the errors made by previous trees. Several advantages, blah blah blah, both linear and nonlinear data. That's highly interpretable. This means that blah blah blah. That the method can be computationally expensive, especially when the number of trees in the model is large. Be sensitive to the choice of hyperparameters such as the learning rate and finding the optimal. This can be prone to overfitting. It's a powerful machine learning technique that can lead to. I think I'm not gonna spend time on this. I'm just gonna read some articles and then just move this there. It's obviously not very well explained. Like, I could go a lot more in depth and explain, but I think it's not worth it. I think I'm only gonna do that if I decide to do that. It's only gonna be after working on several different things, like on blockchain and build stuff and things like that. Then I think that it might be worth going more in depth in the mathematics. And a lot of these algorithms I already know because I studied them in the past when I was doing the Kaggle stuff, Kaggle courses.
Gradient boosting algorithm, a complete guide for beginners. Anshul Sani. Published on September 20th. This article was Introduction. In this article, I am going to discuss the math intuition behind the gradient boosting algorithm. It is more popularly known as gradient boosting machine or GB. It is a boosting method and I have talked more about boosting in this article. Gradient boosting is a method standing out for its prediction speed and accuracy, particularly with large and complex dataset. From Kaggle competitions to machine learning solutions for business, this algorithm has produced the best results. We already know that errors play a major role in any machine learning algorithm. There are mainly two types of error, bias error and variance error. Gradient boost algorithm helps us minimize bias error of the model. Before getting into the details of this algorithm, we must have some knowledge about AdaBoost algorithm, which is again a boosting method. This algorithm starts by building a decision stump and then assigning equal weights to all the data points. Then it increases the weights for all the points which are misclassified and lowers the weight for those that are easy to classify. A new decision stump is made for these weighted data. The idea behind this is to improve the predictions made. I have talked more about this algorithm. Read this article. The main difference between these two algorithms is that gradient boosting has a fixed base estimator, i.e., decision trees, whereas in AdaBoost we can change the base estimator according to our need. Table of contents. What is boosting technique?
So it's pretty much AdaBoost, but with different base estimator. Can change coordinates here. That's pretty much the same thing.
While studying machine learning, you must have come across this term called boosting. It is the most misinterpreted term in the field of data science. The principle behind boosting algorithms is first we build a model on the training dataset, then a second model is built to rectify the errors present in the first model. Let me try to explain to you what exactly does this means and how does this works. Suppose you have n data points and two output classes, 0 and 1. You want to create a model to detect the class of the test. Now what we do is randomly select observations from the training dataset and feed them to model 1, M1. We also assume that initially, all the observations have an equal weight, that means an equal probability of getting select. Remember, in ensembling techniques the weak learners combine to make a strong model, so here M1, M2, M3, Mn all are weak learners. Since M1 is a weak learner, it will surely misclassify some of the observation. Now before feeding the observations to M2, what we do is update the weights of the observations which are wrongly classified. You can think of it as a bag that initially contains 10 different color balls, but after some time some kid takes out his favorite color ball and put 4 red color balls instead inside the bag. Now of course the probability of selecting a red ball is higher. This same phenomenon happens in boosting techniques. When an observation is wrongly classified, its weight gets updated, and for those which are correctly classified, their weights get decreased. The probability of selecting a wrongly classified observation gets increased, hence in the next model only those observations get selected which were misclassified in model 1. Similarly, it happens with M2. The wrongly classified weights are again updated and then fed to M3. This procedure is continued until and unless the errors are minimized, and the dataset is predicted correct. Now when the new data point comes in, test data, it passes through all the models, weak learners, and the class which gets the highest vote is the output for our test data. What is a gradient boosting algorithm? The main idea behind this algorithm is to build models sequentially, and these subsequent models try to reduce the errors of the previous model. But how do we do that? How do we reduce the error? This is done by building a new model on the errors or residuals of the previous model. When the target column is continuous, we use gradient boosting regressor, whereas when it is a classification problem, we use gradient boosting classify. The only difference between the two is the loss function. The objective here is to minimize this loss function by adding weak learners using gradient descent. Since it is based on loss function, hence for regression problems, we'll have different loss functions like mean squared error, MSE, and for classification, we will have different for e.g log likely. Understand gradient boosting algorithm with example. Let's understand the intuition behind gradient boosting with the help of an example. Here our target column is continuous, hence we will use gradient boosting regress. Following is a sample from a random dataset where we have to predict the car price based on various features. For simplicity, we take an average. Step -1. The first step in gradient boosting is to build a base model to predict the observations in the training dataset. Why did I say we take the average of the target column? Well, there is math involved behind this. Mathematically, the first step can be written as. Looking at this may give you a headache, but don't worry, we will try to understand what is written here. L is our loss function. Gamma is our predicted value. Argmin means we have to find a predicted value / gamma for which the loss function is minimum. Since the target column is continuous, our loss function will be. Here E is the observed value, and gamma is the predicted value. Now we need to find a minimum value of gamma such that this loss function is minimum. We all have studied how to find minima and maxima in our 12th grade. Did we use to differentiate this loss function and then put it equal to 0, right? Yes, we will do the same here. Let's see how to do this with the help of our example. Remember that y_i is our observed value and gamma_i is our predicted value. By plugging the values in the above formula we end up over an average of the observed car price, and this is why I asked you to take the average of the target column and assume it to be your first prediction. Hence for gamma equals 14500, the loss function will be minimum, so this value will become our prediction for the base model. Step 2. The next step is to calculate the pseudo residuals, which are observed value, everything. Again the question comes, why only observed? Predicted? Everything is mathematically proved. Let's from where did this formula come from? This step can be written as. Here f, 11, is the previous model and m is the number of dt made. We are just taking the derivative of loss function w.r.t, the predicted value, and we have already calculated this derivative. If you see the formula of residuals above, the predicted value here is the prediction made by the previous model. In our example, the prediction made by the previous model, initial base model prediction, is 14,500. To calculate the residuals, our formula becomes Let's understand this even better with the help of an example. Suppose this is our regressor tree. Image source. We see first residual goes in R1, 1, 2 ND and third residuals go in R2, 1 and fourth residual goes in R3, 1. A gradient boosting classifier is used when the target column is binary. All the steps explained in the gradient boosting regressor are used here. The only difference is we change the loss function. Earlier we used mean squared error when the target column was continuous, but this time we will use log likelihood as our loss function. Let's see how this loss function works. To read more about log likelihood, I recommend you to go through this article where I have given each detail you need to understand this. The loss function for the classification problem is given below. Our first step in the gradient boosting algorithm was to initialize the model with some constant value. There we used the average of the target column, but here if type of EZ underscore add underscore units equals undefined, EZ underscore add underscore units. Gradient boosting works by building simpler, weak prediction models sequentially where each model tries to predict the error left over by the previous model. But what is a weak learning model? A model that does slightly better than random predictions is a weak learner. I will show you the exact formula short, but for clearly bagging, training a bunch of models in parallel way. Each model learns from a random subset of the data, where the data set is same size as original but is randomly sampled with replacement, bootstrapped. Boosting, training a bunch of models sequentially. Each model learns from the mistakes of the previous model. That is, the subsequent models tries to explain and predict the error left over by the previous model. The application of bagging is found in random forests. Random forests are a parallel combination of decision trees. Each tree is trained on random subset of the same data and the results from all trees are averaged to find the classification. The application of boosting is found in gradient boosting decision trees, about which we are. Boosting works on the principle of improving mistakes of the previous learner through the next learner. If in boosting, weak learners, X, decision trees with only the stump, are used. Autoboost uses decision stumps as weak learners. If type of EZ underscore add underscore. In gradient boosting decision trees, we combine many weak learners to come up with one strong learner. The weak learners here are the individual decision tree. All the trees are connected in series and each tree tries to minimize the error of the previous tree. Due to this sequential connection, boosting algorithms are usually slow to learn, controllable by the developer using the learning rate parameter, but also highly accurate. In statistical learning, models that learn slowly perform better. The weak learners are fit in such a way that each new learner fits into the residuals. Till now, we have seen how gradient boosting works in theory. Now, we will dive into the maths and logic behind it so that everything is very clear. Let's discuss the algorithm step by step and make a Python program that applies this algorithm to real-time data. First, let's go over the basic principle behind gradient boosting once again. Your main aim is to predict a y given a set of x. The difference between the prediction and the actual value is known as the residual, or in this case, pseudo-residuals, on the basis of which the gradient boosting builds successive tree. We know this. The algorithm. Let's say the output model y when fit to only one decision tree is given by y equals a underscore 1 plus b underscore 1x plus e underscore 1 y equals a 1 plus b1x plus e1 y equals a underscore 1 plus b underscore 1x plus e underscore 1 where e underscore 1 is the residual from this decision tree. In gradient boosting, we fit the consecutive decision trees on the residual from the last one. So when gradient boosting is applied to this model, the consecutive decision trees will be mathematically represented as e underscore 1 equals a. Note that here we stop at 3 decision trees, but in an actual gradient boosting model, the number of learners or decision trees is much more. Combining all three equations, the final model of the decision tree will be given by y equals a underscore gradient boosting from scratch. Let's consider simulated data as shown in scatter plot below with one input, x, and one output, y, variables. Hashtag the above plot has been generated using the follow. Calculate error residuals. Actual target value, minus predicted target value e1 equals y, y underscore predicted 1. Fit a new model on error residuals as target variable with same input variables, call it e1 underscore predicted.
I think this is the stuff that I was talking about, the randomizing thing.
Stochastic gradient boosting. Stochastic gradient boosting involves subsampling the training dataset and training individual learners on random samples created by this subsample. This reduces the correlation between results from individual learners and combining results with low correlation provides us with a better overall result. A few variants of stochastic boosting that can be used. Subsample rows before creating each tree.
Yeah. I think I'm gonna move on to the next one. Not much to talk about this one. LightGBM is a powerful and efficient gradient boosting framework commonly used for machine learning tasks, particularly for classification and regression design, making a popular choice. It's going to be very similar to the other ones, obviously. Gradient boosting framework that was developed by Microsoft. It's a relatively new framework compared to other popular gradient boosting frameworks such as XGBoost and CatBoost, but it has quickly gained popularity due to its efficiency and scalability. It uses a gradient-based one-side sampling method that reduces the amount of data it needs to process, making it faster and more efficient than other gradient boosting frameworks. Better choice. Firstly, it's faster than these two ones, making it a great choice for large-scale data sets. Has a lower memory consumption, allowing it to handle, finally, parallel and GPU learning, making a great choice for distributed computing environments. Before you start using LightGBM, it's important to make sure you have the necessary software installed. I think I'm gonna delete this part here. Ready to start training. Yeah. Fuck.
To provide the best experiences, we use technologies like cookies to store and/or access device information. Find out more in our privacy policy. Understanding light GBM parameters and how to tune them.
Fuck.
I've been using light GBM for a while now. It's been my go-to algorithm for most tabular data problems. The list of awesome features is long and I suggest that you take a look if you haven't already. But I was always interested in understanding which parameters have the biggest impact on performance and how I should tune light GBM parameters to get the most out of it. I figured I should do some research, understand more about light GBM parameters, and share my journey. Specifically, I took a deep dive into light documentation, went through Lori article. Gradient boosting methods. With light GBM, you can run different types of gradient boosting methods. You have GBDT, DART, and GAUSS, which can be specified with the boosting parameter. In the next sections, I will explain and compare these methods with each other. LGBM GBDT, gradient boosted decision trees. This method is the traditional gradient boosting decision tree that was first suggested in this article and is the algorithm behind some great libraries like XGBoost and PGBRT. These days GBDT is widely used because of its accuracy, efficiency, and stability. You probably know that GBDT is an ensemble model of decision trees, but what does it mean exactly? Read also. Gradient boosted decision trees guide. Let me give you a gist. It is based on 3 important principles. Weak learners, decision trees. Gradient optimization. Boosting technique. So in the GBDT method we have a lot of decision trees, weak learners. Those trees are built sequentially. First tree learns how to fit to the target variable. Second tree learns how to fit to the residual difference between the predictions of the first tree and the ground truth. The third tree learns how to fit the residuals of the second tree and so on. All those trees are trained by propagating the gradients of errors throughout the system. The main drawback of GBDT is that finding the best split points in each tree node is time-consuming and memory-consuming operation. Other boosting methods try to tackle that problem. Dark gradient boosting. In this outstanding paper, you can learn all the things about dark gradient boosting, which is a method that uses dropout, standard in neural networks, to improve model regularization and deal with some other less obvious problem. Namely, GBDT suffers from overspecialization, which means trees added at later iterations tend to impact the prediction of only a few instances and make a negligible contribution towards the remaining instances. Adding dropout makes it more difficult for the trees at later iterations to specialize on those few samples and hence improves the performance. LGBM GAUSS, gradient-based one-side sampling. In fact, the most important reason for naming this method light is using the GAUSS method based on this paper. GAUSS is the newer and lighter GBDT implementation, hence light GBM. The standard GBDT is reliable, but it is not fast enough on large datasets. Hence, GAUSS suggests a sampling method based on the gradient to avoid searching for the whole search space. We know that for each data instance, when the gradient is small, that means no worries data is well trained, and when the gradient is large, that should be retrained again. So we have two sides here, data instances with large and small gradients. Thus, GAUSS keeps all data with a large gradient and does a random sampling. That's why it is called one-side sampling, on data with a small gradient. This makes the search space smaller and GAUSS can converge faster. Finally, for gaining more insight about GAUSS, you can check this blog post. Let's put those differences in a table. It is the default type of boosting. Because GBDT is the default parameter for LGBM, you do not have to change the value of the rest of the parameters for it. Still, tuning is a must. Stable and reliable. Overspecialization, time-consuming, memory-consuming. LGBM DART. Try to solve overspecialization problem in GBDT. Drop underscore seed, random seed to choose dropping models uniform underscore DRO. Set this to true. If you want to use uniform drops boost underscore DART underscore mode, set this to true. If you want to use boost DART mode skip underscore drop. The probability of skipping the dropout procedure during a boosting iteration max underscore drop underscore rate, dropout rate, a fraction of previous trees to drop during the drop, better accurate, regularization. In this section, I will cover some important regularization parameters of light. Obviously, those are the parameters that you need to tune to fight overfit. You should be aware that for small datasets,
These parts of artificial intelligence and machine learning is not that interesting to me. Because the part that is interesting is more about the data and the physics behind the data and how to construct that and to think about consciousness in different ways. So, and this part is more about like tweaking parameters so that in a specific data set you get the best prediction, but it doesn't say anything about the like underlying structure of learning itself. So yeah. I think I'm gonna watch this later.
So my name is Mateusz Sushik. Today I will describe for you two new gradient boosting libraries, like GBM and CatBoost. You might notice that in the title there is a question, and if you know the better reaches law of headlines, usually you might suspect that the answer is no. However, in this case, actually, you might have good reasons to switch to like GBM or CatBoost. Okay, so let's start with a small introduction about me. My name is Mateusz Sushik. I'm currently data scientist at McKinsey & Company here in Warsaw. In the past, I used to work in different places. I used to work at Cenner, I used to work at Mexican Institute. I used to be also a software developer. Currently, I'm doing mostly machine learning. And my today's presentation will split into three parts. Firstly, I will tell you about the XGBoost, the theory behind the XGBoost, how it's implemented. It's crucial because those two new libraries I want to describe, they take inspiration from XGBoost. They're basically more or less the same algorithm with small improvements. So then I will describe the new algorithms, the libraries, and in the end I will show you benchmarks. I have a lot of them. And why do I want to cover those new libraries? So first of all, although they're quite young, they already managed to be very successful in title competitions. So for example, IGBM already won the Sweden Russian housing market contest. CatBoost was in the top of Instacart market basket list, and believe me, those are young libraries. Moreover, I use all of those libraries in my work. I know when to use which of them, and I'm not an author of those, so my comparison will differ. And this also. Okay, so let's start with the theory of gradient boosting. So I hope that you are all familiar with decision tree classifiers. As you know, decision trees work very well with nonlinear data. The problem is that a single decision tree can very easily overfit your data. So here you have an example. This example comes from scikit-learn's recommendation, and you can see that if you build a deep decision tree, it's very prone to outline explanations. So usually people deal with this problem by building ensembles, by using multiple trees. One of the ensembles is gradient boosting. So here's a very nice sketch of gradient boosting. This is something that you can implement if you have a ready to go implementation of decision tree classifier in like half an hour. So what we do, and let me grab a pointer. Okay, so we take our data, y is the dependent variable, we feed a wiki learner, so like a shallow decision tree, then as shown in this example here in the bottom, we end up with some model, so this is square line on this image, and we end up with some error. We call this error residuals, and we do later with another model, so for example here, F2, and we feed it to our residuals only this part here, and we repeat it many times. So H is the model, and Y is our dependent variable. Okay, but this is not actually how XGBoost works. XGBoost is a bit more complicated, and in order to explain it to you, I will follow a very nice introduction by Mr. Tiang Chen. It's called Introduction to Booster Trees. I really recommend it to all of you. So Mr. Tiang Chen is the author of XGBoost, and he firstly observed that, well, if you have an objective classifier, you usually can split it into training loss and regularization term. So in this, for example, we have some classic model. In training loss, we have some error, and in regularization term, we have some L1 here. So here, in order to simplify it, I will use the square loss. And there's one more assumption that we'll do. So if we do k regression trees in gradient boosting, each of the two has its own regularization term. It would be like use only for the tree. Okay, so training gradient boosting is an iterative process. Here I will describe the algorithm trees, and the final prediction is the sum of predictions of all the trees. You can see it here. So we get the first prediction, and then the second prediction, and so on, and we end up with the final model. So we take our formula here. We can, this is our prediction, y hat, so the prediction of the diff after the diff. We can basically analyze the formula and put here our first of all square loss, and then the prediction of the last model and term model. So using the formula of small multiplication, we can analyze further. Moreover, some things will be constant. For example, the y square. This is something we recommend for our example. So we here. And for the prediction trees, you can use any of the one as long as it's differential. So in our case, it's a nuclear and square loss, but if you take our approximation, you can get a standard derivative. Here I will simplify my formula to use g generators to limit on this. And after we move constants, we end up with something like this, yeah? So basically, put filters and change it to generation. One thing is that here is the regularization term. We still have no idea what's our regularization term. So let's check it. So one constant regularization, this is gradient. We need to provide a notion. So in our case, the tree will be a set of leaves. Each leaf will have its own weight. We also call this score. It's a number. And we also function that for each observation tells you in which leaf it ends. Okay? So here is the function that we are the way for scores. So the regularization in XGBoost, the sum is basically sum of L1 and the number of leaf penalties. And now you know that those here you can calculate them. Basically, if you use XGBoost, those are parameters. So this is the number, this is the algorithm, and this is the gamma in XGBoost. On the next slide, I will skip the L1 penalty because the absolute value makes it slightly tough to write down all the other optimizations of the formula. So let's go back to the full formula. We have both the loss, yeah, and the regularization. Nothing changed. Here we sum over all the observations. Here we sum over all the leaves. Each leaf has its own penalty. I mean, the way it's here. So then we can change the slightly order of summing and end up with something like this. Okay? And we can simplify it a bit further using other letters. So now we use uppercase G and uppercase H. And if you have a fixed tree, now it's where it might begin. So if the tree set, this is constant, and we end up with a quadratic function, yeah, where this is a variable W. So then you can optimize it. You can say what's the best value for your leaf, for the weight of the leaf. And basically this is what we end up with. And the most important fact, this is something that will be the conclusion part, is that in gradient boosting on decision trees, like it's implemented in XGBoost, you do not use entropy or information gain for splits. In a decision tree, but use this gain. So what does it represent? So here's the optimal weight of the current leaf that does not get split. Here you have the weight of the possible left sum of the split, and here you have weight optimal.
Light GBM, light gradient boosting machine. Light GBM is a gradient boosting framework based on decision trees to increases the efficiency of the model and reduces memory usage. It uses two novel techniques: gradient-based one-side sampling and exclusive feature bundling (EFB), which fulfills the limitations of histogram-based algorithm that is primarily used in all GBDT. Gradient boosting decision tree framework. The two techniques of Gauss and EFB described below form the characteristics of light GBM algorithm. They comprise together to make the model work efficiently and provided a cutting edge over other GBDT frameworks. Gradient-based one-side sampling technique for light GBM. Different data instances have varied roles in the computation of information gain. The instances with larger gradients, i.e., undertrained instances, will contribute more to the information gain. Gauss keeps those instances with large gradients, example larger than a predefined threshold, or among the top percentiles, and only randomly drop those instances with small gradients to retain the accuracy of information gain estimation. This treatment can lead to a more accurate gain estimation than uniformly random sampling, with the same target sampling rate, especially when the value of information gain has a large range. Algorithm for Gauss. Input, I. Training data, D. Iterations. Input, A. Sampling ratio of large gradient data. Input, B. Sampling ratio of small gradient data. Input, loss function, L. Weak learner. Models. Mathematical analysis for Gauss technique. Calculation of variance gain at splitting feature J, for a training set with n instances x1, xn, where each 11 is a vector with dimension s in space xs. In each iteration of gradient boosting, the negative gradients of the loss function with respect to the output of the model are denoted as g1, gn. In this Gauss method, the training instances are ranked according to their absolute values of their gradients in the descending order. Then, the top A times 100% instances with the larger gradients are kept and we get an instance subset A. Then, for the remaining set AC consisting 1A times 100% instances with smaller gradients, we further randomly sample a subset B with size B times AC. Finally, we split the instances according to the estimated variance gain at vector Vj, D, over the subset A. b, zhd, and the coefficient, 1a, slash b is used to normalize the sum of the gradients over b back to the size of AC. Exclusive feature bundling technique for light GBM. High-dimensional data are usually very sparse, which provides us a possibility of designing a nearly lossless approach to reduce the number of features. Specifically, in a sparse feature space, many features are mutually exclusive, i.e., they never take non-zero values simultaneously. The exclusive features can be safely bundled into a single feature, called an exclusive feature bundle. Hence, the complexity of histogram building changes from O, hashtag data times hashtag feature, to O, hashtag data times hashtag bundle, while hashtag bundle. Hence, the speed for training framework is improved without hurting accuracy. Algorithm for exclusive feature bundling technique. Input, number data, number of data. Input, F, 1 bundle of exclusive features. 0, total bin. 0. For F in, new bin, number data, 0. For J equals 1 to len, fj.bin. Architecture, light GBM splits the tree leafwise as opposed to other boosting algorithms that grow tree level-wise. It chooses the leaf with maximum delta loss since the leaf is fixed. The leafwise algorithm has lower loss compared to the level-wise algorithm. Leafwise tree growth might increase the complexity of the model and may lead to overfitting in small datasets. Below is a diagrammatic representation of leafwise tree growth. Code, Python implementation of light GBM model. The dataset used for this example is breast cancer prediction. Click on this to get dataset, link to dataset, Python. Hashtag installing light GBM, required in Jupyter Notebook and hashtag few other compilers once, pip install light. XGBoost, light GBM, or CatBoost, which boosting algorithm should I use? Gradient boosted trees have become the go-to algorithms when it comes to training on tabular data. Over the past couple of years, we've been fortunate to have not only one implementation of boosted trees, but several boosting algorithms each with their own unique characteristic. In this blog, we will try to determine whether there is one true killer algorithm that beats them all. We'll compare XGBoost, light GBM, and CatBoost to the older GBM, measuring accuracy and speed on 4 fraud-related dataset. We'll also present a concise comparison among all new algorithms, allowing you to quickly understand the main differences between each. A prior understanding of gradient boosted trees is useful. What's their special thing? The algorithms differ from one another in the implementation of the boosted trees algorithm and their technical compatibilities and limitation. XGBoost was the first to try improving GBM's training time, followed by light GBM and CatBoost, each with their own techniques, mostly related to the splitting mechanism. The packages of all algorithms are constantly being updated with more features and capabilities. In most cases, we present the default behavior of the algorithms in R, although other options may be available. In this section, we compare only XGBoost, light GBM, and CatBoost. If you missed GBM, don't worry, you'll find it in the results section. A few important things to know before we dive into details. Community strength. From our experience, XGBoost is the easiest to work with when you need to solve problems you encounter, because it has a strong community and many relevant community posts. Light GBM has a smaller community which makes it a bit harder to work with or use advanced features. CatBoost also has a small community, but they have a great Telegram channel where questions are answered by the package developers in a short time. Analysis ease. When training a model, even if you work closely with the documentation, you want to make sure the training was performed exactly like you meant it. For example, you want to make sure the right features were treated as categorical and that the trees were built correctly. With this criteria, I find CatBoost and light GBM to be more of a black box, because it is not possible in R to plot the trees and to get all of the model's information. It is not possible to get the model's categorical features list, for example. XGBoost is more transparent, allowing easy plotting of trees, and since it has no built-in categorical features encoding, there are no possible surprises related to features type. Model serving limitations. When choosing your production algorithm, you can't just conduct experiments in your favorite environment, R/Python, and choose the one with the best performance, because unfortunately, all algorithms have their limitation. For example, if you use a predictive model markup language, PMML, for scoring in production, it is available for all algorithms. However, in CatBoost you will have to encode categorical features by yourself because its encoding method cannot be converted to PMM. Hence, I recommend taking these considerations into account before starting to experiment with your own data. Now let's go over their main characteristics. Splits. CatBoost uses oblivious decision trees. Before learning, the possible values of each feature are divided into buckets delimited by threshold values, creating feature split pair. Example for such pairs are age, 10, and so on. In each level of an oblivious tree, the feature split pair that brings to the lowest loss, according to a penalty function, is selected and is used for all the levels node. Light GBM uses gradient-based one-side sampling, GAUSS, that selects the split using all the instances with large gradients, i.e., large error, and a random sample of instances with small gradient. In order to keep the same data distribution when computing the information gain, GAUSS introduces a constant multiplier for the data instances with small gradient. Thus, GAUSS achieves a good balance between increasing speed by reducing the number of data instances and keeping the accuracy for learned decision tree. XGBoost offers several methods for selecting the best split. For example, a histogram-based algorithm that buckets continuous features into discrete bins and uses these bins to find the split value in each node. This method is faster than the exact greedy algorithm, which linearly enumerates all the possible splits for continuous features, but it is slower compared to GAUSS that is used by light GBM. Leaf growth. CatBoost grows a balanced tree. Light GBM uses leafwise, best first, tree growth. It chooses to grow the leaf that minimizes the loss, allowing the growth of an imbalanced tree. Because it doesn't grow level-wise, but leaf-wise, overfitting can happen when data is small. In these cases, it is important to control the tree depth. XGBoost splits up to the specified max_depth hyperparameter and then starts pruning the tree backwards and removes splits beyond which there is no positive. It uses this approach since sometimes a split of no loss reduction may be followed by a split with loss reduction. XGBoost can also perform leafwise tree growth, as light GBM. Missing values handling. CatBoost has two modes for processing missing values, min and max. In min, missing values are processed as the minimum value for a feature. They are given a value that is less than all existing values. This way, it is guaranteed that a split that separates missing values from all other values is considered when selecting splits. Max works exactly the same as min, only with maximum value. In light GBM and XGBoost, missing values will be allocated to the side that reduces the loss in each split. Feature importance methods. CatBoost has two methods. The first is prediction values change. For each feature, prediction values change shows how much, on average, the prediction changes if the feature value changes. A feature would have a greater importance when a change in the feature value causes a big change in the predicted value. This is the default feature importance calculation method for non-ranking metrics. The second method is loss function change. This type of feature importance can be used for any model, but is particularly useful for ranking model. For each feature, the value represents the difference between the loss value of the model with this feature and without it. Since it is computationally expensive to retrain the model without one of the features, this model is built approximately using the original model with this feature removed from all the trees in the ensemble. The calculation of this feature importance requires a dataset. Light GBM and XGBoost have two similar methods. The first is gain, which is the improvement in accuracy, or total gain, brought by a feature to the branches it is on. The second method has a different name in each package, split, light GBM, and frequency/weight, XGBoost. This method calculates the relative number of times a particular feature occurs in all splits of the model's tree. This method can be biased by categorical features with a large number of categories. XGBoost has one more method, coverage, which is the relative number of observations related to a feature. For each feature, we count the number of observations used to decide the leaf node for. Categorical features handling. CatBoost uses a combination of one-hot encoding and an advanced mean encoding. For features with low number of categories, it uses one-hot encoding. The maximum number of categories for one-hot encoding can be controlled by the one_hot_max_size parameter. For the remaining categorical columns, CatBoost uses an efficient method of encoding, which is similar to mean encoding but with an additional mechanism aimed at reducing overfit. Using CatBoost's categorical encoding comes with the downside of a slower model. We won't go into how exactly their encoding works, so for more details see CatBoost's documentation. LightGBM splits categorical features by partitioning their categories into two subsets. The basic idea is to sort the categories according to the training objective at each split. From our experience, this method does not necessarily improve the LightGBM model. It has comparable, and sometimes worse, performance than other methods, for example, target or label encoding. XGBoost doesn't have an inbuilt method for categorical features. Encoding, one-hot, target encoding, etc., should be performed by the user. Who is the win? We used 4 datasets in our experiment related to fraud prevention in the e-commerce world, with a binary target variable indicating whether an order made by a customer was fraudulent or legitimate. These example training datasets have around 300 features, a relatively high portion, 1/3, of categorical features and roughly 100k observations. The metric we use is weighted AUC, WAUC, which is similar to AUC but allows the use of different weights to different classes. In our real-world data, we have orders that were declined and we can only partially tag them. Therefore, we gave these orders a lower weight in the AUC calculate. Our adjusted metric will be further presented in a future blog. In all experiments we trained on CPU, using an AWS C4 large instance. Training speed. We compared the training speed, attempting to create as similar as possible conditions to all algorithm. To do this, we trained a model with 4,000 trees and a depth of 1 root node only, with a learning rate of 0.01. The plot below shows the results of the experiment. Each point represents the average of 3 repeated trainings. It is clear that LightGBM is the fastest out of all the other algorithms. CatBoost and XGBoost also present a meaningful improvement in comparison to GBM, but they are still behind LightGBM. For our datasets, LightGBM, CatBoost, and XGBoost were 15x, 5x, and 3x faster than GBM, respectively. Accuracy comparison. We compared the algorithms WAUC on a test set after performing cross-validation hyperparameter tuning across the relevant algorithms parameter. We won't get into the details regarding the chosen hyperparameters, but one thing worth mentioning is that the hyperparameters that were chosen for CatBoost resulted in a more complex model compared to the other algorithms, meaning that the final model almost always had a larger number of trees and a higher depth. The table below shows the test results of the cross-validation experiment. Each cell represents the average WAUC of 5 repeated experiments. In the baseline dataset, CatBoost outperforms the rest by 0.8 to 1%, which is a meaningful difference. In the other datasets, the differences are not as significant, suggesting that accuracy might not be the main criterion when we choose an algorithm for these datasets. So, it's important to take into account other criteria such as speed and technical limitations. Endnotes. After working with all algorithms, we found that unfortunately there is no one winner across all criteria. Therefore, at Riskified, we chose to implement all of them in our systems and select the right one considering the relevant use case. For example, if training speed is our pain point, we use LightGB. In tasks where we need top accuracy, we may train all of the algorithms to find the one with the highest WAUC for that specific dataset. On top of the work we presented here, there are other steps that can be taken for improving accuracy and speed. For improving speed, training on GPUs can be very meaningful. Another important step would be to tune a large number of hyperparameters. There are many hyperparameters that can be tuned in each package, some being exclusive to a specific algorithm. In one of our future blogs, we'll present and compare tuning methods that can be used with boosting algorithms, such as three-phase search and Bayesian optimization. Stay tuned. All packages are constantly being updated and improved, so we recommend following their releases. Gradient boosting vs AdaBoost vs XGBoost vs CatBoost vs LightGBM. Hashtag include using namespace std, int main, coot. Boosting algorithms are one of the best performing algorithms among all the other machine learning algorithms with the best performance and higher accuracy. All the boosting algorithms work on the basis of learning from the errors of the previous model trained and tried avoiding the same mistakes made by the previously trained weak learning algorithm. It is also a big interview question that might be asked in data science interviews. In this article, we will be discussing the main difference between gradient boosting, AdaBoost, XGBoost, CatBoost, and LightGBM algorithms, with their working mechanisms and their mathematics of them. Gradient boosting. Gradient boosting is the boosting algorithm that works on the principle of the stage-wise addition method, where multiple weak learning algorithms are trained and a strong learner algorithm is used as a final model from the addition of multiple weak learning algorithms trained on the same dataset. In the gradient boosting algorithm, the first weak learner will not be trained on the dataset. It will simply return the mean of the particular column, and the residual for output of the first weak learner algorithm will be calculated, which will be used as output or target column for next weak learning algorithm which is to be trained. Following the same pattern, the second weak learner will be trained and the residuals will be calculated, which will be used as an output column again for the next weak learner. This is how this process will continue until we reach zero residual. In gradient boosting, the dataset should be in the form of numerical or categorical data, and the loss function using which the residuals are calculated should be differential at all points. From sklearn.ensemble import gradient boosting XGBoost. XGBoost is also a boosting machine learning algorithm, which is the next version on top of the gradient boosting algorithm. The full name of the XGBoost algorithm is the extreme gradient boosting algorithm. As the name suggests, it is an extreme version of the previous gradient boosting algorithm. The main difference between gradient boosting is XGBoost is that XGBoost uses a regularization technique in it. In simple words, it is a regularized form of the existing gradient boosting algorithm. Due to this, XGBoost performs better than a normal gradient boosting algorithm, and that is why it is much faster than that also. It also performs better when there is a presence of numerical and categorical features in the dataset. From AdaBoost. AdaBoost is a boosting algorithm, which also works on the principle of the stage-wise addition method where multiple weak learners are used for getting strong learners. Unlike gradient boosting and XGBoost, the alpha parameter I calculated is related to the errors of the weak learner. Here the value of the alpha parameter will be indirectly proportional to the error of the weak learner. Once the alpha parameter is calculated, the weightage will be given to the particular weak learners. Here the weak learner that are doing mistakes will get more weightage to fill out the gap in error, and the weak learners that are already performing well will get fewer weights as they are already a good Python 3. From sklearn.ensemble CatBoost. In CatBoost, the main difference that makes it different and better than others is the growing of decision trees in it. In CatBoost, the decision trees which is grown are symmetric. One can easily install this library by using the below command. Pip install CatBoost is a boosting algorithm that performs exceptionally very well on categorical datasets other than any algorithm in the field of machine learning, as there is a special type of method for handling categorical dataset. In CatBoost, the categorical features are encoded on the basis of the output columns. So while training or encoding the categorical features, the weightage of the output column will also be considered, which makes it higher accurate on categorical dataset. Python, LightGBM. LightGBM is also a boosting algorithm, which means light gradient boosting machine. It is used in the field of machine learning. In LightGBM, decision trees are grown leafwise, meaning that at a single time only one leaf from the whole tree will be grown. One can install the required library by using the below. To work with LightGBM also works well on categorical datasets, and it also handles the categorical features using the binning or bucketing method. To work with categorical features in LightGBM, we have converted all the categorical features in the category data type. Once done, there will be no need to handle categorical data, as it will handle it automatically. In LightGBM, the sampling of the data while training the decision tree is done by the method known as GAW. In this method, the variance of all the data samples is calculated and sorted in descending order. Data samples having low variance are already performing well, so there will be less weightage given to the samples having low variance while sampling the dataset. Import light from light import LGB. Which to use? Now it is a very basic question. If all of these machine learning algorithms are the best performing, fast, and gives higher accuracies, then which to use? Well, the answer to these questions cannot be a single boosting algorithm among them, as all of them are the best fit solution for a particular type of problem on which we are working. For example, if you think that there is a need for regularization according to your dataset, then you can definitely use XGBoost. If you want to deal with categorical data, then CatBoost and LightGBM perform very well on those types of dataset. If you need more community support for the algorithm, then use algorithms which was developed years back. Comparison between different algorithms. After fitting the data to the model, all of the algorithms return almost similar kind of result. Here LightGBM seems to perform poorly compared to other algorithms, and XGBoost performs well in this case. To visualize the performance of all the algorithms on the same data, we can also plot the graph between the y_. We can see in the above chart that represents the y_test and y_pred values predicted by every algorithm. Here we can see that LightGBM and CatBoost tend to perform poorly compared to other algorithms, as they are predicting the values of y_pred very higher or lower than other algorithms. XGBoost and gradient boosting perform well on this data, which we can clearly see from the image, as their predictions seem like averaging of all the other algorithms from the graph. Conclusion. In this article, the basic and mathematical difference between gradient boosting, XGBoost, AdaBoost, LightGBM, and CatBoost is discussed with their working mechanism. Knowledge of these differences and core intuitions will help one to understand the difference between them better and help one to answer these types of questions very efficient. Recommended. Solve DSA problems on GFG practice. Solve problem. LightGBM vs Boost. Which algorithm is better? There are a lot of data enthusiasts who are taking part in a number of online competitive competitions in the domain of machine learning. Everyone has their own unique independent approach to determine the best model and predict the accurate output of the given problem statement. In machine learning, feature engineering is very much an integral part of the process and also consumes most of the time. On the other hand, modeling becomes an important part where you cannot have much pre-processing or have certain constraints on the features. There are different ensemble methods that help in making strong, robust models that can give very accurate prediction. But exactly what is this buzz of the word ensemble? Let us understand what the term ensemble means in detail. Ensemble. Before moving into a technical definition straight away, let us take a simple real-life example and understand the same. Let us assume that you want to buy an electronic device, mobile phone. Your first approach would be searching on the internet about different latest smartphones and comparing rates of different companies. You will also see the features in different models. After this first step, you will ask your friends about their opinion about the mobile phones which you have shortlisted. In this fashion, you will take opinions and suggestions from a couple of people. Once you get a couple of positive reviews about a particular mobile phone, you will go ahead and buy that mobile phone. This is the exact concept of the term ensemble. Ensemble methods is a machine learning technique in which several base models, weak learners, are combined in order to produce one powerful model. Let us now go further into detail with the boosting method. Boosting is one of the sequential ensemble techniques. This technique is usually applied to the data with high bias and low variance. Here we have a dataset D with n records. We take LGBM is a quick, distributed, and high-performance gradient lifting framework which is based upon a popular machine learning algorithm, decision tree. It can be used in classification, regression, and many more machine learning tasks. This algorithm grows leafwise and chooses the maximum delta value to grow. LightGBM uses histogram-based algorithms. The advantages of this are as follows. Less memory usage. Reduction in communication cost for parallel learning. Reduction in cost for calculating gain for each split in the decision tree. So as LightGBM gets trained much faster, but also it can lead to the case of overfitting sometime. So, let us see what parameters can be tuned to get a better optimal model. To get the best fit, following parameters must be tuned. Number_leaves. Since LightGBM grows leafwise, this value must be less than 2 carat. Max_depth. To avoid an overfitting scenario. Min_data_in_leaf. For large datasets, its value should be set in hundreds to thousands. Max_depth. A key parameter whose value, for achieving better accuracy, following parameters must be tuned. More training data added to the model can increase accuracy. Can be also external unseen data. Number_leaves. Increasing its value will increase accuracy as the splitting is taking leafwise, but overfitting also may occur. Max_bin. High value will have a major impact on accuracy but will eventually go to overfit. A very popular and in-demand algorithm often referred to as the winning algorithm for various competitions on different platforms. CatBoost stands for. This algorithm is an improved version of the gradient boosting algorithm. The base algorithm is gradient boosting decision tree algorithm. Its powerful predictive power and easy to implement approach has made it float throughout many machine learning notebooks. Some key points of the algorithm are as follows. It does not build the full tree structure but builds it greedily. As compared to LightGBM, it splits level-wise rather than leaf-wise. In gradient boosting, negative gradients are taken into account to optimize the loss function, but here Taylor's expansion is taken into account. The regularization term penalizes from building complex tree models. Some parameters which can be tuned to increase the performance are as follows. General parameters include the following. Booster, it has two options, tree and blink. Silent, if kept to one, no running messages will be shown while the code is executing. And thread, mainly used for parallel processing. The number of cores is specified. Booster parameters include the following. ETA, makes model robust by shrinkage of weights at each step. Max_depth, should be set accordingly to avoid overfit. Max_leaf_nodes, if this parameter is defined then the model will ignore max_depth. Gamma, specifies the minimum loss reduction which is required to make a split. Lambda, L2 regularization term on the weights. Learning task parameters include the following. 1. Objective, this will define the loss function which is to be used. Binary, logistic regression for binary classification, returns predicted probability, not the class. Multi, softmax multi-class classification using the softmax objective, returns predicted class, not the probabilities. Learn about the random forest algorithm and how it can help you make better decisions to reach your business goals. Random forest is a commonly used machine learning algorithm trademarked by Leo Breman and Adele Cutler, which combines the output of multiple decision trees to reach a single result. Its ease of use and flexibility have fueled its adoption, as it handles both classification and regression problems. Decision trees. Since the random forest model is made up of multiple decision trees, it would be helpful to start by describing the decision tree algorithm brief. Decision trees start with a basic question, such as, should I surf? From there, you can ask a series of questions. Ensemble methods. Random forest algorithm. The random forest algorithm is an extension of the bagging method as it utilizes both bagging and feature randomness to create an uncorrelated forest of decision tree. Feature randomness, also known as feature bagging or the random subspace method, link resides outside IBM.com, PDF, 121 KB, generates a random subset of features, which ensures low correlation among decision trees. This is a key difference between decision trees and random forests. While decision trees consider all the possible feature splits, random forests only select a subset of those features. If we go back to the should I surf example, the questions that I may ask to determine the prediction may not be as comprehensive as someone else's set of questions. By accounting for all the potential variability in the data, we can reduce the risk of overfitting, bias, and overall variance, resulting in more precise prediction. Random forest algorithms have three main hyperparameters, which need to be set before training. These include node size, the number of trees, and the number of features sampled. From there, the random forest classifier can be used to solve for regression or classification problems. The random forest algorithm is made up of a collection of decision trees, and each tree in the ensemble is comprised of a data sample drawn from a training set with replacement, called the bootstrap sample. Of that training sample, 1/3 of it is set aside as test data, known as the out-of-bag (OOB) sample, which we'll come back to later. Another instance of randomness is then injected through feature bagging, adding more diversity to the dataset and reducing the correlation among decision trees. Depending on the type of problem, the determination of the prediction will vary. For a regression task, the individual decision trees will be averaged, and for a classification task, a majority vote I.e. The most frequent categorical variable will yield the predicted class. Finally, the OOB sample is then used for cross-validation, finalizing that predict benefits and challenges of random forest. There are a number of key advantages and challenges that the random forest algorithm presents when used for classification or regression problem. Some of them include key benefits. Reduced risk of overfitting. Decision trees run the risk of overfitting as they tend to tightly fit all the samples within training data. However, when there's a robust number of decision trees in a random forest, the classifier won't overfeed the model since the averaging of uncorrelated trees lowers the overall variance in prediction. Provides flexibility. Since random forest can handle both regression and classification tasks with a high degree of accuracy, it is a popular method among data scientists. Feature bagging also makes the random forest classifier an effective tool for estimating missing values as it maintains accuracy when a portion of the data is missed. Easy to determine feature importance. Random forest makes it easy to evaluate variable importance, or contribution, to the model. There are a few ways to evaluate feature importance. Gini importance and mean decrease in impurity, MDI, are usually used to measure how much the model's accuracy decreases when a given variable is excluded. However, permutation importance, also known as mean decrease accuracy, MDA, is another importance measure. MDA identifies the average decrease in accuracy by randomly permutating the feature values in OOB sample. Key challenges. Time-consuming process. Since random forest algorithms can handle large data sets, they can provide more accurate predictions, but can be slow to process data as they are computing data for each individual decision tree. Requires more resources. Since random forests process larger data sets, they'll require more resources to store that data. More complex. The prediction of a single decision tree is easier to interpret when compared to a forest of them. The random forest algorithm has been applied across a number of industries, allowing them to make better business decisions. Some use cases include finance. It is a preferred algorithm over others as it reduces time spent on data management and pre-processing tasks. It can be used to evaluate customers with high credit risk, to detect fraud, and option pricing problems. Healthcare. The random forest algorithm has applications within computational biology. Link resides outside IBM.
I think I'm gonna leave this because it seems to be correct. I think I'm gonna remove this one. I think I'm gonna leave this article like this, move on to the next.
Random forest classifier, a complete guide to how it works in machine learning. All you need to know about the random forest model in machine learning. Random forest is a flexible, easy-to-use machine learning algorithm that produces, even without hyperparameter tuning, a great result most of the time. It is also one of the most used algorithms. Due to its simplicity and diversity, it can be used for both classification and regression tasks. In this post, we'll cover how the random forest algorithm works, how it differs from other algorithms, and how to use it. What is random forest? Random forest is a supervised learning algorithm. The forest it builds is an ensemble of decision trees, usually trained with the bagging method. The general idea of the bagging method is that a combination of learning models increases the overall result. Table of contents. How random forest work. Real-life analogy. Feature importance. Difference between decision trees and random forest's important hyperparameters, predictive power, speed. Advantages and disadvantages of the random forest algorithm. Random forest use cases. How random forest works. Random forest is a supervised learning algorithm. The forest it builds is an ensemble of decision trees, usually trained with the bagging method. The general idea of the bagging method is that a combination of learning models increases the overall result. Put simply, random forest builds multiple decision trees and merges them together to get a more accurate and stable prediction. Building, using and evaluating random forest's video, StatQuest with Josh Starmer. One big advantage of random forest is that it can be used for both classification and regression problems, which form the majority of current machine learning systems. Let's look at random forest in classification, since classification is sometimes considered the building block of machine learning. Below you can see how random forest would look like with two trees. Random forest has nearly the same hyperparameters as a decision tree or a bagging classifier. Fortunately, there's no need to combine a decision tree with a bagging classifier because you can easily use the classifier class of random forest. With random forest, you can also deal with regression tasks by using the algorithm's regressor. Random forest adds additional randomness to the model while growing the tree. Instead of searching for the most important feature while splitting a node, it searches for the best feature among a random subset of features. This results in a wide diversity that generally results in a better model. Therefore, in a random forest, only a random subset of the features is taken into consideration by the algorithm for splitting a node. You can even make trees more random by additionally using random thresholds for each feature rather than searching for the best possible thresholds, like a normal decision tree does. V127 jobs find out who's hiring in Austin. See all data plus analytics jobs in a real-life example of random forest. Andrew wants to decide where to go during his one-year vacation, so he asks the people who know him best for suggestion. The first friend he seeks out asks him about the likes and dislikes of his past travels. Based on the answers, he will give Andrew some advice. This is a typical decision tree algorithm approach. Andrew's friend created rules to guide his decision about what he should recommend, by using Andrew's answers. Afterward, Andrew starts asking more and more of his friends to advise him, and they again ask him different questions they can use to derive some recommendations for. Finally, Andrew chooses the places that recommend the most to him, which is the typical random forest algorithm approach. This in-depth tutorial will help you to even better understand random forest algorithms. Random forest feature importance. Another great quality of the random forest algorithm is that it is very easy to measure the relative importance of each feature on the prediction. Sklearn provides a great tool for this that measures a feature's importance by looking at how much the tree nodes that use that feature reduce impurity across all trees in the forest. It computes this score automatically for each feature after training and scales the results so the sum of all importance is equal to 1. If you don't know how a decision tree works or what a leaf or node is, here is a good description from Wikipedia. In a decision tree, each internal node represents a test on an attribute. Example, whether a coin flip comes up heads or tails. Each branch represents the outcome of the test, and each leaf node represents a class label, decision taken after computing all attributes. A node that has no children is a leaf. By looking at the feature importance, you can decide which features to possibly drop because they don't contribute enough, or sometimes nothing at all, to the prediction process. This is important because a general rule in machine learning is that the more features you have, the more likely your model will suffer from. While a random forest is a collection of decision trees, there are some differences. If you input a training dataset with features and labels into a decision tree, it will formulate some set of rules, which will be used to make the prediction. For example, to predict whether a person will click on an online advertisement, you might collect the ads the person clicked on in the past and some features that describe their decision. If you put the features and labels into a decision tree, it will generate some rules that help predict whether the advertisement will be clicked or not.
I think I'm not gonna include this one. I'm not gonna include this. I'm just gonna delete. Actually, Boost already read a bunch of stuff. I'm just gonna review the article. It's probably gonna be very similar to the other ones. I think I'm gonna finish this shoe stop, and then I'm gonna review more articles off stream about the other categories. And watch these videos here.
This page was generated from doc/user_guide/random using random survival forests hashtag. This notebook demonstrates how to use random survival forests introduced in Scikit Survival 0.11. As its popular counterparts for classification and regression, a random survival forest is an ensemble of tree-based learners. A random survival forest ensures that individual trees are decorrelated by 1, building each tree on a different bootstrap sample of the original training data, and 2, at each node, only evaluate the split criterion for a randomly selected subset of features and threshold. Predictions are formed by aggregating predictions of individual trees in the ensemble. To demonstrate random survival forest, we are going to use data from the German Breast Cancer Study Group, GBSG2, on the treatment of node-positive breast cancer patient. It contains data on 686 women and 8 prognostic factors: 1 age, 2 estrogen receptor, esterag, 3. Whether or not a hormonal therapy was administered, 4th, menopausal status, may no stat, 5. Training hashtag. Several split criterion have been proposed in the past, but the most widespread one is based on the log rank test, which you probably know from comparing survival curves among 2 or more group, using the predicting hashtag. For prediction, a sample is dropped down each tree in the forest until it reaches a terminal node. Data in each terminal is used to non-parametrically estimate the survival and cumulative.
Random forest.
Stochastic gradient boosting (SGB) is a powerful machine learning algorithm that has been gaining popularity in recent years due to its ability to achieve impressive results in a variety of applications. I've been working on SGB. I think this one I already saw as well, a long time ago. And boosting is an assemble technique, blah blah blah. You know, the loss function for a given model, just in the model. This should be the gradient is calculated for each iteration using a random subset of the training data. It's very similar to the other ones. I'm just gonna pass this one, honestly. I think it's not worth reading the articles. I know that it is correct, all of this stuff. Obviously the quality is not great because it's not explaining anything about the source code, but I'm gonna leave it like this for now. So let's look at the other one. Image, speech, from image and speech recognition, natural language processing models. It's one of the most popular and effective field machine learning. Performance, blah blah blah. Let me search for this one.
XGBoost. XGBoost is an open source XGBoost, which stands for Extreme Gradient Boosting, is a scalable, distributed gradient boosted decision tree (GBDT) machine learning library. It provides parallel tree boosting and is the leading machine learning library for regression, classification, and ranking problem. It's vital to an understanding of XGBoost to first grasp the machine learning concepts and algorithms that XGBoost builds upon: supervised machine learning, decision trees, ensemble learning, and gradient boost. Supervised machine learning uses algorithms to train a model to find patterns in a dataset with labels and features, and then uses the trained model to predict the labels on a new dataset's feature. Decision trees create a model that predicts the label by evaluating a tree of if-then-else true/false feature questions and estimating the minimum number of questions needed to assess the probability of making a correct decision. Decision trees can be used for classification to predict a category, or regression to predict a continuous numeric value. In the simple example below, a decision tree is used to estimate a house price, the label, based on the size and number of bedrooms, the features. A gradient boosting decision trees, GBDT, is a decision tree ensemble learning algorithm similar to random forest for classification and regression. Ensemble learning algorithms combine multiple machine learning algorithms to obtain a better model. Both random forest and GBDT build a model consisting of multiple decision trees. The difference is in how the trees are built and combined. Random forest uses a technique called bagging to build full decision trees in parallel from random bootstrap samples of the dataset. The final prediction is an average of all of the decision tree predictions. The term gradient boosting comes from the idea of boosting or improving a single weak model by combining it with a number of other weak models in order to generate a collectively strong model. Gradient boosting is an extension of boosting where the process of additively generating weak models is formalized as a gradient descent algorithm over an objective function. Gradient boosting sets targeted outcomes for the next model in an effort to minimize errors. Targeted outcomes for each case are based on the gradient of the error, hence the name gradient boosting. With respect to the predict, GBDTs iteratively train an ensemble of shallow decision trees, with each iteration using the error residuals of the previous model to fit the next model. The final prediction is a weighted sum of all of the tree predictions. Random forest bagging minimizes the variance in overfitting, while GBDT boosting minimizes the bias in underfit. XGBoost is a scalable and highly accurate implementation of gradient boosting that pushes the limits of computing power for boosted tree algorithms, being built largely for energizing machine learning model performance and computational speed. With XGBoost, trees are built in parallel, instead of sequentially like GBDT. It follows a level-wise strategy, scanning across gradient values and using these partial sums to evaluate the quality of splits at every possible split in the training set. Why XGBoost? XGBoost gained significant favor in the last few years as a result of helping individuals and teams win virtually every Kaggle structured data competition. In these competitions, companies and researchers post data after which statisticians and data miners compete to produce the best models for predicting and describing the data. Initially, both Python and R implementations of XGBoost were built. Owing to its popularity, today XGBoost has package implementations for Java, Scala, Julia, Perl, and other languages. These implementations have opened the XGBoost library to even more developers and improved its appeal throughout the Kaggle community. XGBoost has been integrated with a wide variety of other tools and packages such as scikit-learn for Python enthusiasts and Caret for R user. In addition, XGBoost is integrated with distributed processing frameworks like Apache Spark and Dask. In 2019, XGBoost was named among InfoWorld's coveted Technology of the Year award winner. XGBoost benefits and attributes. The list of benefits and attributes of XGBoost is extensive and includes the following: a large and growing list of data scientists globally that are actively contributing to XGBoost open source development, usage on a wide range of applications, including solving problems in regression, a library, cloud active, a library that was built from XGBoost and data scientists. It's noteworthy for data scientists that XGBoost and XGBoost machine learning models have the premier combination of prediction performance and processing time compared with other algorithms. This has been borne out by various benchmarking studies and further explains how XGBoost runs better with GPUs. CPU-powered machine learning tasks with XGBoost can literally take hours to run. That's because creating highly accurate, state-of-the-art prediction results involves the creation of thousands of decision trees and the testing of large numbers of parameter combination. Graphics processing units, or GPUs, with their massively parallel architecture consisting of thousands of small efficient cores, can launch thousands of parallel threads simultaneously to supercharge compute-intensive tasks. Hi, my name is Microsoft Mark. English, boosting, especially of decision trees, is among the most prevalent and powerful machine learning algorithms. There are many variants of boosting algorithms and frameworks implementing those algorithms. What is XGBoost? The term XGBoost can refer to both a gradient boosting algorithm for decision trees that solves many data science problems in a fast and accurate way and an open source framework implementing that algorithm. To disambiguate between the two meanings of XGBoost, we'll call the algorithm XGBoost the algorithm and the framework XGBoost the framework. To understand XGBoost the framework, we first have to understand XGBoost the algorithm. What is XGBoost the algorithm? As the name may reveal, XGBoost the algorithm is a gradient boosting algorithm, a common technique in ensemble learning. To unpack that new phrase, ensemble learning is a type of machine learning that enlists many models to make predictions together. Boosting algorithms are distinguished from other ensemble learning techniques by building a sequence of initially weak models into increasingly more powerful models. Gradient boosting algorithms choose how to build a more powerful model using the gradient of a loss function that captures the performance of a model. Gradient boosting is a foundational approach to many machine learning algorithms. XGBoost has solidified its name in the boosting game with its use in many competition-winning models and prolific reference in research. How does XGBoost the algorithm work? XGBoost the algorithm operates on decision trees, models that construct a graph that examines the input under various if statements, vertices in the graph. Whether the if condition is satisfied influences the next if condition and eventual prediction. XGBoost the algorithm progressively adds more and more if conditions to the decision tree to build a stronger model. How does XGBoost the algorithm work? XGBoost the framework implements XGBoost the algorithm and other generic gradient boosting techniques for decision trees. XGBoost the framework is maintained by open source contributors. It's available in Python, R, Java, Ruby, Swift, Julia. XGBoost the algorithm was first published by University of Washington researchers in 2016 as a novel gradient boosting algorithm. Like other gradient boosting algorithms on decision trees, XGBoost considers the leaves of the current decision tree and questions whether turning that leaf into a new if statement with separate predictions would benefit the model. The benefit to the model depends on the if statement chosen and which leaf it's placed on. This can be determined using the gradient of the loss. The loss includes a scoring function that measures algorithm performance. Get to know other data science students. Samuel Okoye, read story. Mencken, data scientist at WhatsApp. What sets XGBoost the algorithm apart? XGBoost the algorithm sets itself apart from other gradient boosting techniques by using a second-order approximation of the scoring function. This approximation allows XGBoost to calculate the optimal if condition and its impact on performance. XGBoost the algorithm can then store these in its memory the next decision tree to save recomputing it. XGBoost the algorithm is powerful on its own but is also a great fixer-upper using the other tools from your machine learning toolbox. Consider feature engineering for instance, where the machine learning engineer pre-processes the raw inputs into new input features before letting the model get its hands. XGBoost the algorithm makes the most of engineered features and can produce a nicely interpretable and high-performing model. How do you use XGBoost? Together, XGBoost the algorithm and XGBoost the framework form a great pairing with many uses. XGBoost the algorithm learns a model faster than many other machine learning models and works well on categorical data and limited datasets. XGBoost the framework is highly efficient and developer-friendly and extremely popular among the data scientists community with lots of documentation and online support. These advantages make XGBoost, both the algorithm and the framework, useful for many machine.
I'm gonna leave it like this. Yeah, I'm gonna leave it like this. Then I think I'm gonna stop here. And I'm probably gonna do another category. I think I'll do the easy categories first. And then after some time, I'm gonna go back to studying blockchain and building the articles for blockchain. If I just review most of them, I think I can finish all of them before I go back to blockchain stuff. So I'll probably do the stack and 2 pointers off stream. Try to finish them today. And I'm gonna do what maybe I'll do arrays and hashing actually. Arrays and hashing in 2 pointers. I think those are the easiest ones probably. Stack, because they're the ones that I already did some problems and I studied a lot. Binary search should be easy as well. Yeah, so I think what I'm gonna do is try off stream. I'm just gonna do the same thing that I'm doing now, which is pretty much just check the facts and check if the information is correct, but I'm not gonna change much, and I'm just gonna try to go as fast as possible until I finish all of this. And then on the blockchain articles, I'm gonna spend more time, a lot more time, studying stuff and also building things like that. And I might work on the poker algorithm again, on the poker software that I was working on the past. So yeah, probably gonna come back tomorrow and keep reviewing these articles here until I finish all of them. So